statistics, you have this section directly on statistical physics. I mean, that's
yeah. But this is the online, the first online scientific congress of SIFS.
Oh, I see.
That actually is the 25th Congress of Statistical Physics. And so it's just a continuity with respect to the previous years. But it's really the first national congress, and it is online for obvious reasons, and we hope that the next year it will not be online, because we have enough, certainly have enough to be online for everything. We gain some advantage, but I think that it's very hard to go on and meet people and interact in this way. I mean, at least I'm not used to, and
maybe I can add, Herbert, the Italian Physical Society that exists is not like the DPG. So the DPG is much more structured. So all subtopics are represented within the DPG. So the Italian Physical Society has a structure which is not always represents all the subtopics. That's why the Italian Society for Statistical Physics has been created as an independent association in collaboration, which we are collaborating clearly with the
yes, moreover, it's not the only one. There are more than 20 such societies in Italy beyond SIF.
Oh, I see. So SIF is just sort of so.
Yeah, is the general one, and then
yes, I see. Yeah, back home it's sort of more structured. I mean,
yeah, we have our own activities. Fortunately, we hope to have common activities that are not only congresses. But you see, in this situation, it's very hard to really co-organize things, and everything is very complicated by many problems. And
it will come again. I mean, so.
Yeah.
Roberto, I think we can start, because we are already more than 70 participants. So you can start your address at the society.
Yes, I don't want to spend too much time. I was just mentioning before that this is the first Italian Congress of the Italian Society of Statistical Physics, Complex Systems, and actually it is also the 25th Congress of Statistical Physics of Complex Systems that was usually held in Parma, and which is really a very important event for all our community. Now we are proceeding along this tradition by this new container, this new opportunity, this new Congress. And we have decided to organize online this Congress because it is important for the visibility of our community and its relation at international level. And I was really amazed by the number of people that applied to attend this Congress. It's really a gigantic number that would be very hard probably to collect altogether in the usual place that we are used to occupy in Parma to work for this kind of Congress. I think that this is really this testifies the vitality of our research area. And I want to stress that a lot of young people also applied to this Congress. And this makes me confident that for the future, not only the activity that we have been organizing during this pandemic era, but also for the future, this community will grow and profit a lot of also of these opportunities. Tomorrow, there will be, I want to recall to everybody that at least the associated to the SIFS, that we have our National Assembly, yearly National Assembly, where we have to take some important decisions. And I hope that all the people which are entitled to participate will participate. And today, I think that we have a very interesting program to attend. And I want to congratulate the scientific committee and the organizing committee that made a very good job in selecting the talks and also selecting from the many proposals. Actually, there were really a lot of proposals. All of you know that some reduction was in some sense in order to make the duration of the Congress reasonable. Anyway, as I wrote to all of you, all those who submitted proposals, we take care for the future of the proposals that this year were not able to be represented by any kind of talk. As you know, we have some invited talks, and also we have some shorter talks. And I want to remember that we have also a special section of Ignite talks. And in the next days, we'll attend also interesting poster sessions that are organized and subdivided into rooms where you can find a sort of, how to say, guiding person for all who are entering the room and want to have information about the posters presented there. So I think that I have already taken a lot of time, and I want to welcome all of you to this Congress. And I think it's time to start with the first speech of this afternoon, which is given by Professor Herbert Spohn from the Technical University of Munich. And he's going to present a very interesting topic, also in particular, very interesting to me, which is hydrodynamic equations for integrable many-body system, the case of the classical Toda lattice. So please, Herbert, it's your...
Okay, so I share my screen here.
Yeah.
And let's see, this should work usually.
Yeah.
Can you see? I mean, is it
perfect?
Should I make it larger? Is it a good size? Or?
Yes, that's the right size.
That's fine.
Yeah.
Okay. So Roberto, I mean, thank you very much for this kind introduction. I hope everybody can hear me. I mean, that's sort of loud enough, or okay. So yeah, no, I'm very much pleased, I mean, to be able to attend this meeting and for the opportunity to explain some of my recent results. And what I've been working on is sort of a fairly you know, lots of people have been working on this. I mean, that's the hydrodynamic equations for integrable systems. Of course, it's very much pushed by the quantum community. Now, hydrodynamics is, of course, an old subject, and started with sort of dynamics of fluids. I mean, Euler, these people, I mean, you know, they could look at the real fluid and somehow guess what are the correct equations on a macroscopic scale. But since then, of course, hydrodynamics has been sort of, you know, applied to many other systems. But the idea to apply hydrodynamics to integrable systems is actually quite recent. I mean, that's about the major sort of starting papers are sort of 5 or 6 years back. Now, what one could do, or what I might have done, is sort of, you know, give you some of the highlights. Of course, you know, there are experiments, and particularly sort of systems like the delta Bose gas or maybe quantum spin systems, which can be realized experimentally, and then you know, tell you sort of some of the equations. But I think for a short talk and at the end, I mean, presumably would sort of not really get so much out of it. And so I decided to do a totally different strategy. I will sort of, you know, disregard all the beautiful other work which has been done, but I thought that I concentrate on one single system, which is the classical Toda lattice, which is sort of presumably, you know, the best understood, I mean, you know, non-trivial system. I mean, it's not an ideal gas, it's a strongly interacting system. And I think that has the advantage that, you know, you can focus directly on the system. And I hope what I would like to transmit is, you know, what are the sort of theoretical problems which I have to solve in order to figure out what are the correct hydrodynamic equations. And then there will be applications. Of course, I cannot treat everything in a short time. So let me start with reminding you of the Toda lattice. I mean, so this was motivated by the fact that for continuum nonlinear wave equations, you have soliton solutions, and Toda was asking the question whether something similar could be happening if you look instead of a continuum wave equation, you look at sort of spatially discretized wave equation, sort of like a harmonic chain. And after some thoughts, I mean, he came up with this beautiful observation that if you take a chain which has an exponential potential, so particles sort of repel with this exponential force or exponential potential, and that this system happens to be integrable. Now, he first found soliton solutions, and later on there was more structure, and I will come to this. So here's my Hamiltonian. I mean, so you have the usual kinetic energy. So the advantage of the Toda lattice is it's classical. So I mean, Italy, you still have professors for analytical mechanics, so I can assume that everybody knows about classical mechanics. And so that's one of the advantages of discussing the Toda lattice, that there's not too much sort of, theoretical overhead. Anyway, so here is my Hamiltonian. Here I write Newton's equation of motion, forces from the right and from the left. I mean, the positions are arbitrary on the real line. There's no ordering between particles, and they have their own momenta. Of course, it's not a permutation invariant system. It's sort of what people call a chain, in the sense that particles with label J and J+1 are actually interacting. Okay, so it's not a really true one-dimensional fluid, but sort of like an anharmonic chain. There's no free parameter. People like to put some parameters here, but this you can all scale out. So you can just really focus on that particular question. There's a question somewhere. I mean, somebody raised his hand. I mean, I'm happy to answer the question if this is technically feasible. No, okay. Anyway, so you let me know if there are questions.
Oh, it's feasible. Yes. Don't worry.
Okay. All right. Okay, so here are other models. I mean, quantum-vector freezes are continuum wave equations. You have, of course, the quantum mechanical models. There's also a quantum version of Toda lattice. So let me think about sort of a physical picture. So one of them is that one thinks these particles really moving on the real line. I mean, this is what we call the Toda fluid. But then can also put sort of more this point of view of nonlinear wave equation. If you sort of make a naive continuum limit of this equation, then this you have to get this difference becomes just a derivative, and then you see it's sort of a nonlinear wave equation with somewhat funny nonlinearity. It's sort of this function is just the exponential function. Okay? So the next thing I want to show you is sort of a little picture here of 20 Toda particles on a circle, and I want to emphasize that much of the work which people have done refers to the Toda particles on the infinite lattice, and of course on the infinite lattice. Or what's happening is that particles repel, and eventually sort of they sort of propagate off to infinity, completely independent. Maybe with a shift, but anyway, I mean they sort of separate at large times. Now I want to do hydrodynamics, and of course, like for a real fluid, you put them in a container. I mean you don't want to evaporate, and so this is what I have done in this picture. So the time is to the right, and now you can see this motion of particles. The thing which I want to emphasize is that it's far from being pair interactions. I mean, here you have a nice interaction, sort of, two particles colliding and sort of doing the usual two-body motion. But then here you see you have a whole strings of sort of more complicated objects. And anyway, so it's this system which we want to look at. And since it's sort of confined, I mean, you can hope that if you start with some, let's say, randomly picked initial condition, if you sort of wait long enough, eventually, you will reach some sort of stationary state. And maybe if you're lucky enough, I mean, there is sort of there are slow degrees of freedom, which actually sort of can be described in terms of some autonomous equations. Now, that's fairly vague. I just want to emphasize that, confining the system, I mean, let's say superperiodic boundary conditions is crucial for the kind of physics I want to study. All right, so now let's see what we want to do. And I sort of, despite the fact that I might repeat, I sort of want to sort of remind you a little bit of the ordinary hydrodynamics, which you would do for one-dimensional fluids, since the integrable systems are all in one dimension. So let me do the example already in one dimension. So here is a simple fluid, and I just want to sort of tell you, what is sort of the basic physics assumption behind writing down the Euler equations for one-dimensional fluids. Of course, these things have been used. I mean, for instance, when people try to estimate the explosion of the atomic bomb, I mean, then the way how they did the estimation is they actually solved these one-dimensional Euler equations. Anyway, so now for one-dimensional fluid, the dynamics is very chaotic, and so you expect that there are only 3 conservation laws, which is of course mass, momentum, and energy. And the idea is that you start with random initial data, which are already constructed in such a way that the system is sort of in local equilibrium, which means roughly the following. So here I've sort of put for you a picture. So this is sort of, you know, some variation, let's say, in the temperature on the macroscopic scale. And if I take a little fluid element and I enlarge enormously, what I will see is sort of course, a bunch of particles, but they have a very precise statistic, which is given in terms of what we know from equilibrium statistical mechanics. Of course, the parameters like inverse temperatures or the density or the mean velocity, they depend on the particular space-time patch I'm looking at. But wherever I look, you know, with a rather good approximation, provided this is not changing and sort of has a slow variation, it's not changing on atomic scale, but sort of on a larger scale, it will be sort of a distribution which given by you know, the well-known formula. But I just wanted to point out one important thing, that what you have to do in hydrodynamics is you have to sort of, you know, in order to specify the state, you have to take all the parameters. So in our case, we have really 3 parameters. And so what you have to take is sort of the inverse temperature for the energy. Then there will be a chemical potential for the number of particles. And there must be, because, you know, the particles can move, there must be a parameter which I call U for the mean velocity. And the main point, which of course Gibbs knew already and sort of very well known, is that once I sort of use a grand canonical prescription, which makes sense because I'm looking at the small subsystem, then the correct distribution we have to do is you have to first know the conserved quantities, and then you just take a linear combination. And then, you know, the parameters of these linear combinations are, so to speak, the parameters which labeled the stationary states in this case, right? And so now you, once you know that this is the correct local distribution, it's clear what you have to do is, I mean, you compute with this distribution what is the average fields, what's the average mass, momentum, and energy, and you also compute the average currents. Now, once you have this, I mean, then of course you can express, you know, now you have sort of objects which depend on 3 parameters, and you can express the average currents in terms of the average fields. This I don't want to do. This is what I call task 1 here. And this is a computation which you have to do in global equilibrium. Okay, now assume that you have done this computation, so you know how the average fields depend, how the average currents depend on the average fields. Then you basically assume that this situation is propagating in time. I mean, this is what, you know, usually is called sort of propagation of local equilibrium. This kind of situation, which I sort of explained here for one space-time patch, is actually sort of propagating in space-time. And now you have to write down the field equations. Of course, you know, I mean, this should maybe do for the field averages. Anyway, then there is sort of the task 2 to actually somehow justify the fact that you know, this local equilibrium is actually propagating. This is what I call task 2, and the task 2 is very difficult. It's very difficult for real fluids. It's very difficult for one-dimensional fluid. It's also very difficult for integrable systems. And I will just disregard task 2 completely, except for the fact that, you know, when I write down my equations, I will assume this kind of local equilibrium. Okay. So let me just repeat that task 1, which is purely thermodynamics, is depending a little bit, but, you know, I could regard this as, so to speak, the easy case. Task 2 involves really, you know, knowing some more details about the dynamics, which is typically difficult, and you will see some signs of this later on. Okay, so now let's come to the hydrodynamics of integrable systems. Now, first of all, it's just a big guess. I mean, that you know, this kind of scheme, which we know to work extremely well for strongly interacting non-integrable systems, should also work in the somewhat sort of, you know, extreme case of systems where you have an extensive number of local conservation laws. I mean, integrable systems are characterized by the fact that they don't have only 3 conservation laws, but, you know, they have, if you make the system of size n, I mean, they have n conservation laws. And so this is really the central theoretical difficulty. I mean, you know, how can I deal with a system which has an extensive number of local conservation laws? Now, the big guess, which of course everyone who seriously would think about this, I mean, you know, might try to do, you know, at least as a first attempt, is that you simply close your eye and say, well, let's just simply use the same strategy as for simple fluids. So let's just do the simple scheme, which I was in the case of 3 parameters. Let's just do it now for the huge number of chemical potentials which I need in order to label all these conservation laws. Okay, so you see what we really have to do is we have to sort of investigate sort of I put here statistical mechanics of the Toda lattice. This might be a little bit confusing, but you will see in a second. I mean, when I talk about statistical mechanics, I mean that I have to include all the conservation laws, not just the first 3 of them. Okay, so this is the major sort of first theoretical difficulty, which you have to somehow understand how to do. How do I deal with this large number of local conservation laws? Okay, and so you will see that on the dynamics, I have very little to say, but on this static point, I can give you sort of some illumination. Okay, so let's do a little bit sort of statistics. So when I talk about statistical mechanics, I don't mean necessarily thermal equilibrium. I mean, it will be something which people call generalized Gibbs ensembles. I mean, Gibbs ensembles which depend on a very large number of parameters, but there will be no dynamics. There will be partition functions and then thermal expectations and such kind of things. Okay, so let's first do what you learned from the little picture, namely, we want to put periodic boundary conditions, and the proper way to put the periodic boundary conditions is that you sort of think of a cell of size L, and there you put a certain number of particles, and then you just repeat it periodically. I mean, that's sort of the way how it's done. And you see that when I take a given configuration, then in the next cell I have to add this parameter. In the next cell I have to add this parameter. Next cell I have to add this parameter L. Okay, and L, of course, physically is a very important quantity because it's sort of is the control parameter for the density of particles. So you better should not forget about this. Okay, so I have one conserved quantity which comes with this. We'll come to the next slide. All right. So now if you want to do this. If you want to do this hydrodynamics, I mean, you have to somehow know about the conservation laws. And fortunately for the Toda lattice, I mean, this is sort of known since the early days, I mean, 1974. And the main trick, which sort of goes to back to Flaschka, who was at the Courant Institute and somehow learned this as a student, sort of more or less automatically, is that these things become easy if you're able to construct something which people call the lax matrix. And so let me just sort of explain to you this a little bit. So first of all, you sort of rewrite the equations in terms of slightly different variables. You introduce the stretch, which is simply the difference between particles with a neighboring index. Again, the RJ doesn't have to be positive, can be both positive, negative. But then you form the HA, which is the exponential with this 1/2 of the difference. And the HA, of course, these are positive variables. And then you rewrite these equations in terms of these new variables. I mean, then it looks like this. You see now, sort of, you lose a little bit the physics. It becomes sort of much more algebraic. I mean, now you have the A's, and this is sort of a quadratic function of the P's, and here it's also quadratic. But you see, it's sort of like a chain. I mean, it's sort of like a lattice field theory. I mean, so this term gives you the interaction to the right, and this term gives the interaction to the left. And so you can also think of what sort of my picture at the moment is that you think sort of a one-dimensional lattice. At every lattice size, you have these field degrees of freedoms, which are positioned, and the A variable, I mean, the Flaschka variable, so the stretch variable, and of course, they sort of are in a circle. So you have just the usual periodic boundary condition, as you would guess immediately. Okay. Now the next thing. So now you want to look at conserved quantities. So conserved quantities for finite system are just sort of some functions on phase space which doesn't change in time. But this is not good enough. And in particular, even for quantum mechanical systems, the situation would be even worse, presumably, than here in this particular system. The point is that we don't want to have all possible imaginable conservation laws. Hydrodynamics is built on the idea that the conservation laws should be local. And since it's such an important idea, I sort of want to give you sort of one very simple example, and something which I need anyhow. So let's just do it. I mean, so on the basis of these equations of motion, you you just plug it in here, you realize that the sum over the RJs, I mean, the sum of the stretches is actually conserved. So here you have a function on phase space which doesn't change in time. But you see, I mean, obviously it has a density. I mean, it's the sum of local things, it's just sort of single side objects. And when I now take the derivative of the local field, then it has this conservation type. I mean, it's some other function, but shifted by one lattice unit. So that's sort of a discrete lattice derivative. And it's those conservation laws which we need. And it's those conservation laws for which you will a hydrodynamic picture. Okay, so that's the locality. So you have a local field and you have the corresponding local current and you have this sort of lattice conservation type equation. All right. Okay, so now what about the other conservation laws? Now, of course, you immediately guess the momentum. Of course, it's a conservation law that you see directly, and then energy. But there will be more. And then how do you even write down the more? And the more you write down, this is sort of this beautiful idea. By out of the dynamical variables of your system, you form a matrix, and this matrix is arranged in such a way that along the diagonal you put the momenta, and to make it periodic, you get the a n. Well, the off diagonal are the a's. That's the exponential of the stretch, and to make it periodic, I mean, you have to put the a n over here, and then there's sort of a system matrix. This is why it's sometimes called the Lex pair. And that's sort of the anti-symmetric version. I mean, the diagonal is 0, and then you put the a's again as before, but with a minus sign. Okay, so this generates a unitary evolution, and that's just, of course, just the matrix as given. Okay, and now you observe that the equations of motion, which you've written down, when you sort of evolve all these coefficients according to our Toda lattice dynamics, then you see that the time derivative of the Lex matrix is given by this commutator. And out of this, because this generates a unitary, you see that the eigenvalues, I mean, so it's a symmetric matrix, as you can see, it has eigenvalues and eigenvectors. The eigenvalues are necessarily conserved. That's just because, under unitary evolution, I mean, it moves complicated, but the eigenvectors sort of move, but the eigenvalues are not changing in time. But the eigenvalues of this matrix are highly non-local. If I change a little bit the A over here, you will get a totally different eigenvalue. So this is no good. Eigenvalues are not local. But this is what Plaschka observed already. What you can do is you can actually produce a very easy local version. And the idea is that you just take the trace of this matrix to some arbitrary power, which is little n. I mean, n is the lattice sides, and little n is sort of the label of the conserved quantity. And so you see when you plug in the numbers, I mean, when you take, n equals 0 is sort of different, but when you take n equal to 1, I mean, then this gives you the momentum. If you take n equal to 2, this gives you the energy, and then you get higher orders. And you see that because it's a trace, you can write it sort of, you sum along the diagonal elements of this matrix, and so it's obviously a sum. So this would be the candidate for the local field. But since the matrix is tridiagonal, I mean, this is of course, it just is a finite sum. And since it's such an important thing, I mean, let me do this simple computation for you. I mean, so let's take n equal to 6, and let's look at one of these things. I mean, when you work out this product of matrices, you can represent this in terms of sum over random walks. It's tridiagonal, so you go either up or you go down, or you stay constant, and then you take such a lattice path. Because I do JJ, the initial point and the final point have to be the same. And as I go up, this gives an A0. Here's another A, so it gives A0 squared. That's a P1, that's a P1, and then it's another A1 squared. So this particular random walk corresponds to a polynomial which is given by this object. And now you do the sum over all walks, then you get a somewhat more complicated polynomial, and this will be the conserved quantity. It's not so interesting to look at what the 20th conserved quantity looks like, but it's important to have a formula which you can analyze. Okay, and so I call this density, I give the label n here, I call this density the Qn. Okay, and then for the currents, there's something similar, but because I will have no time to do the currents, I mean, let me just sort of sketch it. Okay, so now you want to understand the long time limit, and as Boltzmann told you, what you would expect is that you know, it's an integrable system, and if you're Hamiltonian in terms of the action variables, it doesn't have any flat pieces, which in this case is actually a mathematical theorem which you can prove. Then what you know, there are the frequencies on this invariant torus are incommensurate, and eventually you will just converge to the uniform Lebesgue measure on the tori. So in this case, for an arbitrary size system, you know what the long time asymptotics of the system will do. It will just go to this uniform measure. But to analyze these invariant tori, I have no idea. And so now you do something which is sort of, of course, well known from statistical mechanics. Rather than doing this, you know, would correspond to the microcanonical ensemble, you're fixing all the conserved quantities, which I don't know how to handle. You sort of switch immediately to the grand canonical prescription, and this I do know how to handle. Okay, so let's see how to do this. So I'm using here, you know, sort of a somewhat fancy version of equivalence of ensembles. And the first thing what I do is I do the equivalence of ensembles for the sum of the stretches. You see, in my original prescription, I force them to be some given number, which now I make, because system size should be proportional to n, I make them proportional to n. So this I don't know how to handle, but then, you know, if I go to the grand canonical, it's just the exponential of this with a new parameter, which is e to the minus p times rj. And now I'm very happy. Of course, you know, this p, which is the pressure, should be positive. And so you see now, if you think about the potential which I have in my chain, is that I have the e to the minus r from Toda, so that's which is going down. But now, you know, because I do this constraint, I get an e to the plus positive p rj, and so it will be a straight line like this. So you get a stable situation. Of course, if I make p negative, then everything flies apart, and that's not a good idea. So this is sort of step one. I mean, that I get a nice formula for when I go to the grand canonical prescription, and from this you get automatically the a priori measure. This one corresponds to the p. It's just sort of written in terms of this a variable, and then you have to do a little bit of change of variables. The p's are as before, and the a's, you know, it's the exponential function, so I pick up this extra factor. So you have, instead of the usual dp dq, you have now a new a priori measure, but which is still a product. I mean, so you know, you have your lattice system. And if I do the a priori and nothing else, I mean, then I sort of see this is sort of the distribution. And of course, you know, this is constructed in such a way that it doesn't change under the dynamics. It's just like you know, for system of particles, the Lebesgue measure, you know, the volume measure doesn't change under the dynamics, and the same thing over here. And it's a pure product. Okay, so this is just like what you're used to when you sort of teach some basic course in statistical mechanics. This is sort of the first step. Okay, now we have to do the interaction. Okay, now I emphasize that when we do Gibbs statistical mechanics, I should take the linear combination of all conserved quantities. Well, okay, so let's just do it. I mean, so here's the exponential. Here's the sum over all the conserved quantities. They just differ by this power n. And it's the Lax matrix to the power n and its trace. And so I can push the sum under the trace, and then you see that what I have to do is I have to take the exponential of minus of trace of some function of Ln. Now, when you look at this, I mean, you want to have this function stable. So, you know, it should be a function maybe like this, or maybe you want to stop the series after, let's say, up to kappa equal to 4. I mean, then, you know, you would have a quartic polynomial. I mean, so you know, then it would look something like this maybe. Okay, but in general, it's some general function which should sort of increase at infinity, and therefore, you know, I like to kind of call it a confining potential. I mean, it will be confining later on. I mean, but the main point is that you know, if you want to have a stable system, it really should be confining. Okay, so now we have the Boltzmann weight, and then you do what people nowadays call generalized Gibbs ensembles. I mean, generalized just means that you know, there are more parameters than what you are used from thermal equilibrium. I mean, the special case of thermal equilibrium corresponds to taking L to be linear and quadratic, so only n equal 1 and 2, right? But then now we have to take all the higher order things, and the generalized Gibbs ensemble is this very beautiful formula. Here's the a priori, and the Boltzmann weight is given by this exponential of the trace of some confining function, which you should think of like a quartic function, maybe of the trace of the Lax matrix. Okay, so let's count the parameters. You see, we have one parameter which is the pressure, which appears here. But then the Gibbs weight is indexed by a full function. Okay, it can be a finite polynomial, but it's better to think of this as a full function. So now you see that our generalized Gibbs ensembles are sort of a more complicated thing because you know, it's not just one or two parameters which vary, but there are many. Okay, so this I told you already. So in the thermal case, it becomes very simple, and you just IID Gaussian random variables. Okay, so let's skip this thing for the sake of time. But let's look at this thing here. This is sort of a very important insight, and so now let me sort of say a few words about this. You see, when you look at these dynamics, and then you look at the conserved quantities, I mean, it's not so intuitive, and there's another way of actually looking at this problem, which is you know, it doesn't help in terms of solution, but it's actually sort of, you know, in terms of description, is much more natural. And of course, it's something which, you know, people who have done, you know, random matrices or so, you see the Lax matrix is now random under our GGE, right? I mean, so it's a matrix, but the entries of this matrix are random. Now, the natural thing to do is to look at what people call the density of states. I mean, so you see the density of states is sort of the most natural and simple objects you can imagine. So I give one particular configuration. So this gives me a particular Lax matrix. I compute the eigenvalues, and then I take these eigenvalues, and each eigenvalue I simply weigh by with a factor 1/n, right? I mean, so this gives me sort of like a discrete, you know, sort of probability distribution, which is sitting on n different points. Okay. Now, what I emphasize is that the individual eigenvalues, you know, they might float around a lot. I mean, so if I start changing my parameters, you know, they change very widely. But the object which is sort of unsensitive and something which in the long time limit becomes non-random is actually this sum. So this is a normalized probability distribution, normalized to 1. It's positive because I have here all these delta functions. It's random still because if I start changing my input parameters from the GGE, it's going to change. But when I make the system large, it will go to a deterministic asymptotic quantity, right? I mean, so, you know, you should think of this sort of looks maybe sort of like a Gaussian, or of course can be more complicated, but you should think of this as a sort of reasonably nice distribution. Now, what is the point about this distribution? What is the point about this Lax density of states? Is that once I know this, then of course I know exactly the quantity which I need for my hydrodynamics. Namely, if I look at the moments, if you look at, you know, the L to the N and how I did this construction, you see that when I look at the GGE average of my nth conserved quantity is nothing else but the nth moment of this density of state. So rather thinking about discrete index and sort of, you know, discrete numbers and those things which sort of maybe not structurally, maybe not so pleasant, it's much better to look at this quantity here, which is sort of the central quantity, right? I mean, and of course, once I have this, then if I compute the moments, then I can, in particular, the lower order moments, I can get the physical quantity of interest. Okay, so since time is limited, I mean, let me just say at this stage already, you know, what is actually the physical picture behind, you know, behind this new insight. So here, you know, I prepare my Toda particles, and, you know, maybe I have on the big computer, and I do 10,000 or maybe 20,000. I let them run, and then the question is, and I take this sort of, you know, fairly random initial data, and the question is, what am I going to see at time t? Now, of course, at time t, you want to sort of see the things which you know, there will be a lot of noisy motion, but sort of on a large scale, there should be something which is sort of changing only slowly in time. But what is this object which is changing slowly in time? Well, it's the local density of states. So you see what I do is, so of course I can do this, I need a computer to do this. You know, it's not so easy to do it experimentally, but conceptually, I think this is what you should do. I let the system evolve. I look at, let's say, a little subset of labels, let's say 300 or 400. Okay. Now, for the given configuration at time t, I evaluate this density of states. I mean, so I have to compute the eigenvalues, but then I form the density of states. And it's this density of states which is a slowly varying quantity. If I if I look at some neighboring cells, I will see some other density of states, but it's not changing dramatically, but it's changing smoothly from one cell to the next. And also when I look at some later time, it will be still that density of state which has been changed. And it's that density of state which is governed by a somewhat complicated nonlinear evolution equation, which maybe at the end I can still write down. But this is sort of the mental picture which you should have. I mean, these conserved quantities can be easily organized in terms of this density of state together with the stretches, so that's one axis parameter, and it's this quantity which has a slow motion and which has an autonomous equations of motion. Okay, so let's go still a little bit into this problem a little bit further, and let's do sort of the very first exercise, which of course you somehow have to do, but this is the one thing which I'm looking on my watch here, but this is one thing which I would like to do, and then presumably I have to jump ahead and come to the end. Okay, so now you see that we have this beautiful partition function. Okay, well, I just have to integral over that, but of course, I mean, you're totally stuck. I have just no idea how to do this. I mean, this is nice, but this is an awfully complicated object, right? I mean, I have just no idea. Now you see what would be very helpful would be that if somehow I would know something about this distribution of eigenvalues under this thing, because this trace depends only on the eigenvalues. So this cannot be done. But then now there's sort of a somewhat surprising sort of known result in the literature by Dumitru and Edelman, sort of from random matrix theory, and they proved that. Think of this just as a mathematical identity. This is why I put here the B's and A's instead of the P's. Just think of this as a mathematical identity. And then what they proved quite some time ago, 2002, is the following identity. So you see this sort of our a priori. Here's e to the trace of Tn. I modified my matrix a little bit, but not very much. I just left out the one here at the two edges, and then this certainly will not change very much the free energy. Okay, so I'm doing sort of more or less the same. And then they claim that they, by some miraculous transformation, they can actually transform this into something which we know from statistical mechanics very well. I mean, it's a one-dimensional log gas. So you have here the d lambda. Okay, it's the exponential of the V. The V appears here. So this is sort of the distribution of the eigenvalues of this random matrix and of this particular random matrix. And then from the volume element, you get this logarithm. Okay, a much studied object in statistical mechanics. All right, so this looks great. So you say you're done, but now you have to look at the small print, and the small print is that this parameter is changing linearly in J. So the pressure, before this was just the pressure, now the pressure is changing linearly in space. And so you're stuck. I mean, this, of course, it's a nice formula, but this is not what we want to have. We want to have a constant pressure. I mean, physically, of course, it's a constant pressure for which you do this sort of the GGE. So how do I go from this one to the other? And now the simple solution is, and amazingly simple solution is to say, you see, there is this free parameter. And their theorem is true whatever positive beta you pick. It's just a mathematical identity. And now let's choose beta in a very clever way. And the most obvious clever way is to choose beta as twice the pressure divided by 1 over n. Okay, so now let me put it in here. And now you see that now, this ramping, this linear ramping has a slope of 1 over n only. And therefore, if I look at the little piece of this partition function here, it will look like a constant pressure. Hooray, I'm done. But you see, there's a further simplification, namely, the beta, which here was sort of like a strong interaction, sort of, you think of beta as written, just something like 1. Actually, now the beta becomes 2p divided by n. So actually, I have an interaction which goes like 1 over n. So I get 2 bonuses. One of them is that locally it looks like the measure I want to know. And secondly, this object, which is still sort of not totally trivial, now simplifies because I have this extra p over n. It's not manufactured by me. It's just sort of, an idea how you can. Well, it's manufactured by me, but it's manufactured in such a way to solve the problem. Right? It's not starting with a mean field model, but you sort of are led to picking beta like 2p over n. Okay, so once you do this, then you see that things sort of fall into the place. Namely, when I take the partition function, I mean the free energy of this modified model, at each point it will be just the Toda, so it will be the integral over the Toda. But this thing I can compute because, you know, you can just write down the corresponding free energy function, and this is how you get it. Okay, so you see this is linearly in the density of states, and this is of quadratic in density of states. And so the answer is that we find here a mean free functional, which has a logarithmic interaction. It's this linear term, and then of course there's the usual entropy. And if I want to know the free energy, then I have to compute the minimizer, which happens to be unique in this case. And now you have to be a little bit sort of manipulating, namely, if you want to get the Toda free energy, you know, because of this ramping, it's not just the mean field free energy evaluated at the minimizer, but what you have to do is you have to take this mean field free energy computed at a minimizer, you have to multiply it by P, and you have to then take to the derivative with respect to P. Okay. All right. So this is what you find, and so what we have achieved here is that the free energy of the Toda lattice, the generalized free energy, in a very natural way, is expressed in terms of solution of the variation problem. Now, of course, this is something which people observed also for other systems. You know, there's the famous Liebniger delta Bose gas, the Young Paper. What they discovered, what they argued, is that when I look at the free energy, I mean, at this time, you know, they didn't think about generalized, but it would be also for the generalized case. I mean, they looked just at the quadratic confining potential, but, you know, this extends to general confining potential. What they found already, you know, in the mid-50s, they found already that this particular integrable system has a free energy given in terms of a variation, sort of a variation problem of free energy function. And so here I'm just observing exactly the same thing for the Toda lattice. Okay, it's a general fact about these integrable systems. Okay, so let me not go into this. And so let me sort of sum up with sort of you know, but what we find at the end. I mean, so now one has to do something about the carbons, which you know, for the lack of time I couldn't tell you, but this can be done. And so now let me just sort of tell you what the equations are which you get at the end. I mean, so here is now my Toda lattice, and I'm looking, you know, a huge number of particles. This is now a space-time continuum, and when I take here a little cell, then eventually I will see the lattice. But then the assumption is that whatever statistics of particles I see here is given by GGE, so it will be governed by the inverse of the average density, which is this new at this space-time point xt, and also by the space-time changing lag density of states. Okay, so these are the two parameters which sort of characterize what I'm going to see locally. You see now it's a full function. I mean, here's a function of W. This is a number, but here you have a function which depends on laxity, and that, of course, has to satisfy conservation law. And the conservation law, there's one which sort of, it's sort of like mass conservation. So there's this one, first one, and you see that's linked to the first moment of this lax density of state. And then there is just a function, there's just an evolution equation for the whole density of state. So you look at the time change of this density of state, that's given by some object which you know, I will explain in a second, and that's equal to 0. So you get sort of this set of conservation laws. So it's just like an Euler equation. And the object which is here sort of slightly complicated. And so you know, I cannot really go into details, but I guess all what I want to say in the next slide here is that it looks bad, but it's not too bad. I mean, you know, you have to sort of somehow invert this type of integral operator. So if you really want to do solutions, I mean, then one option would be just sort of, you know, do a numerical simulation by discretizing, and this is doable. So I mean, you have to sort of know a little bit how to do it, but eventually you should think that you know, these equations are complicated, but they're certainly amenable to you know, to fairly high precision numerical simulations, which, you know, don't take the age of the universe. I mean, you know, this is something which nowadays computer, I mean, you have to specify the problem more precisely, but, you know, there are lots of simulations around which I cannot show you. Okay, so let me come to the conclusions and summary. So if you want to know more about Toda, I mean, I posted lecture notes. I mean, where you find many details, presumably more than you ever want to know. But just for those people who want to look up a little bit, I mean, you can turn the pages more slowly than I do this in the talk. I mean, so you can see some of the constructions if you are more interested sort of in the integrable quantum many-body, another which I sort of even advise sort of a little bit more than reading this one is sort of very nice lecture notes by Benjamin Doyon. Actually, he also uses quite a bit the Toda because it itself the explanations, but he emphasizes sort of the unity. I mean, you know, the same scheme you find sort of in different integrable systems. And these are very nicely written. Then there's a special volume of study about emergent hydrodynamics of integrable many-body systems, which is going to appear there. You will find more than you ever want to know. And the final thing which I want to emphasize is that there is this universality, which sort of, you know, people are still working on this. It's sort of, to me, still very much surprising that once you're on this large scale, then you have forgotten much of the original system. You see, despite the fact you're looking at very different systems like the Toda, and then you look maybe at some I don't know, XXC quantum chain, it has sort of still very much the same structure. And what is left over is only, you know, of course, whether the system is quantum or classical. I mean, that's somehow because thermodynamics becomes different. So that, of course, makes a difference. And the real dynamical input into these equations is a two-particle scattering shift. I mean, that's all these higher order things by some magic sort of disappear, and the final equation remembers only the two-particle scattering shift. Okay, then now your Stokes corrections. I want to thank you for listening.
Thank you, Herbert. I am unmuting myself. So I think we are really short in time. There is probably one space for just one question before passing to the next speaker. By the way, I want to thank Herbert again for the very nice seminar. If anybody is interested, want to make a question, please, you can unmute and make that. I don't hear anybody. So I have one question, very, very fast question. So you showed us that there is a way to approach hydrodynamics for this kind of model, which is Toda is not, as you were saying at the end of your speech, a peculiar case. So there might be many other situations where you can find similar situations. But I think that all these models should share at least one common feature. They should be interacting in some sense, so the non-linear, if you want. I was thinking that, for instance, the Ablovitz-Laddick model could be a good candidate to check if this universality is still there. Very good, Roberto. I was sort of prepared for this question because I knew that you would ask about Ablovitz. I have been working about the Ablovitz-Laddick sort of, you know, for the recent months, and I can tell you the answer is yes. And the only difference is that, you know, for the Ablovitz-Laddick, these eigenvalues are not sitting on the real line, but they're actually sitting on the unit circle. And on the unit circle, we still have this log gas. So rather than having the log gas on the line, you find that you get the log gas on the unit circle. And then you can do Ablovitz-Laddick. The defocusing case of Ablovitz-Laddick. The focusing case, I don't know how to do. I see. Okay, so, but there is some hope that all these structure is a sort of universal or general. Very much. I mean, this is open and we are working on this. I mean, you can also look at, you know, Carloccio Motors models and, you know, take a guess what should be the hydrodynamics. You know, the theory has developed to the level that you know, because you only need the two-particle scattering shift, that you can guess what are the equations, right? But then the question is, you know, I mean, do the steps in between, right? Yeah. No, the belief is that in all these models, it should be short. You know, it should be short range somehow. Right? So it's not for long range models, right? I mean, the Toda is sort of, you know, a type thing, right? It should be short ranged. I mean,
But the 1/sin squared of Garlaschelli motor should be also fall under this scheme. Yes.
Okay, thank you very much. And I think that it's time, if there are no other questions that should be done immediately, we could pass to the following speaker of the this first session, who is actually Massimo Cencini, who is going to speak about learning to hide and seek at low Reynolds numbers.
Hi, Roberto. I slightly changed the title. You will see why, but it's very similar. So I don't know how to remove this. Okay, maybe I put it here. Okay. So first of all, I would like to thank the scientific committee and the organizers for letting me have the opportunity to speak about this work, which I have done in collaboration with Francesco Borra, Luca Biferale, and Antonio Celani. I want to stress that Francesco, who is doing the PhD in Rome, was the true engine of this work, which, as you can see from the picture, speak about someone who wants to catch someone else, and the latter that want to escape. But this is in an hydrodynamic environment. So just a little bit of motivation. So in this movie, you see a fish who is swimming, avoiding brilliantly some Lego obstacles. The striking fact is that this fish is completely blind, as you can see from the picture below, and is able to do this thanks to essentially its ability to sense the hydrodynamic field. You see on the left, the fish, a typical fish, has the so-called lateral line. All the black spots you see are essentially mechanosensors which are able to sense variation of pressure and other properties of the fluid. And these are usually very useful, for example, to navigate in dark water, like in a cave, or to sense the prey or the predators when they are not in view, for example. And humans are starting to somehow emulate biomimetically these sensors in underwater robotics, which is used a lot in the last few years. Coming to smaller animals, like for example copepods, they have antennae setae whose bending when excited by a flow, like for example when a predator is approaching, allow these animals to somehow sense the presence of the predator, and this elicits an escape response, as you can see in the movie. For example, is conjecture that the copepods are able to sense the gradients of the velocity field. The problem is that when you have a small Reynolds number involved, like when you have small microswimmers, usually the hydrodynamical signals are rich of symmetries and so of ambiguities. And a next step for the inspiration of this work is something that has been done in OpenAI. They have implemented a multi-agent reinforcement learning approach to the problem of hide and seek. That's the old name of the paper, of the talk. And this is there are two opponents: the seeker and the hider. They can both use tools to accomplish their goal. And with this kind of learning techniques, essentially they learn a lot of things. Also to discover, as you can see from the movie, the wrong design of the physics of the system. Like the seeker, at a certain point, jump on the square and is able to. Yeah, you can see now this is wrong in physics, but because it was designed by wrongly. So all these things more or less inspired us to analyze the prey-predator interactions you have, which I describe now, you have two swimmers, two micro swimmers. You can model them as like swimming first dipole. So while swimming, they deform the fluid, creating a flow. Is a pusher-like, so water is pushed from the head and tail of the swimmers, like for bacteria, and is going towards the swimmer on the lateral. They have a swimming velocity. They generate a velocity field. Each swimmer swims by its own self-propulsion, but also due to the field induced by the other. The pursuer wants to search for the other, the predator for the prey, and it can only slightly maneuver its heading direction by slightly imposing a thrust, so an angular velocity, either to the left or to the right, or just go straight. And to inform each other on their position and their motion, they can only rely on hydrodynamic cues that we assume to be just the velocity gradients. So essentially, the pursuer can perceive the velocity gradient of the velocity induced by the evader, and vice versa, and vice versa. So the game is as follows. They start at the distance 1, random heading direction. Each time tau, time interval tau, they sense the gradients, and depending on what they sense, they choose which action to take. The goal of the predator is to catch the prey, so to reach a distance below a given value in an amount of time less than Tmax, while the evader win only if the game exceeds Tmax. So they have two opposite goals. One wants to minimize the game duration, and the other wants to maximize it. So this is just to express in dynamics what I said in words. So the dynamics of the pursuer is its own self-propulsion plus the advection due to the flow induced by the evader. The self-propulsion is in the direction theta p, which can be modified, is modified by the vorticity induced by the evader and by the actions. So the angular velocity is able to use, which is simply three values. I don't give details on the velocity just to not lose time, just give you the idea that the velocity depends as the inverse of the distance, and the micro swimmers can sense the gradients. Gradients depends on the square inverse of the distance, and essentially are three components: the longitudinal, shear, and vorticity. And this show the kind of deformation they induced. Without focusing too much on the questions, you see that the information that you can grasp from the gradients are a combination of some angles, which is expressed here, a proxy of the distance that you can obtain, for example, from the square of the square root of the sum square of these two components, and the vorticity, which mix a bit information of angle and distance. So these angles are the so-called bearing angle, which is essentially the angle between the heading direction of one swimmer and the position of the other, and vice versa for the other swimmer. This is essentially the information you would get if you just see, you could see the other. And then this is the relative heading direction. And you can see that you cannot have access to the single of this angle, but you can only access a combination of them. And this is a problem. This is a problem because given the symmetries of these equations, you cannot distinguish these four configurations of the evader. For example, the pursuer cannot distinguish these four configurations. So you have limited control and you have partial information. How to cope with this to learn efficient strategies? The idea is to use reinforced learning, as we have saw briefly for the OpenAI problem. So I have no time to provide the full details on the algorithm, but I want to at least convey you the main idea. So you have an agent. The agent is our microswimmer in our case. He receives observation from the environment, the gradients, the gradients. this observation is used to choose an action, essentially through a policy, which is the probability of taking an action A given the observation of the system O. This action is taken for is maintained for a given time interval tau. Then new observation come, and together with the reward, something which tell you if the action you have taken is good, led you to a good situation or to a better situation or to a worse situation. Essentially using the observation of the previous time, the new observation after you've taken the action, and the reward, you can understand how to update, how to improve your policy in such a way to maximize the expected cumulated reward. The policy which maximizes this essentially provides you the best strategy you can do to for your goal, which is in the case, in our case, to maximize or minimize the duration of the game. These are some references for the precise algorithm we used. I just want to give the name, natural actor critic. Essentially is a graded sense of a space of policy which are parameterized in some way. And so what are the actions we already see are the possibility to turn. The observations are what you can grasp from the gradient, which are codified by these quantities. And the rewards, essentially each time step, the pursuer receive a -1 because he has to minimize the time. So he receive a penalty. While the other receive +1 because he's incentivized to let the game duration to last as much as possible. A last detail on the way we implemented the learning scheme. So we started with random policy. So each action is taken independently of the observation, probability 1/3. And we organize the learning in cycles. So we started with the pursuer. We keep fixed the policy of the divider to the random one. And the pursuer has a given number of games through which he can improve his policy to so devise his strategies to minimize the time to catch its prey. We considered, for example, 500 games. Then the policy, the strategy of the pursuer is fixed to the one that is obtained at the end of this cycle of learning, and the others start to learn how to defend from those strategies. And then again and again, exchanging the role of the various agents. As I said, each cycle is made of 5,000 games, which usually in the language of reinforced learning are called episodes. And the episode is the one that I described before. Start a given distance, random orientation, take your actions. And the point is that you learn while playing. So at each moment you take an actions and observations, you get the new observation and the reward, and you learn. You update your rules. These are the parameters we used. Before not focus on the precise numbers, just on the idea. The idea is that we choose parameters such that for distances less of the order of the initial distance, hydrodynamics start to be important. The smaller the distance, the more hydrodynamics is important with respect to self-propulsion. And we give them more or less the same maneuverability conditions. So the radius of curvature they can do is the same. This is three realization of the process with the random seeds. And the picture here shows the rewards, average rewards over a certain number of episodes to eliminate some fluctuations in a few cycles. You see that the first two cycles are quite reproducible. The pursuer basically is able to decrease in its learning cycle. Then the other start to re-increase the game duration, so it starts to win some time. Then something strange happens and there is some variability, which we haven't understood completely. Maybe it's due to some instability in the code, in the bad choices of the parameter, and combined with the fact that as more as the strategies become complicated, the exploration to find new strategies is more complicated. This is the picture of where they start. They start from random strategy. So most of the time is on like here. So random searching should be very inefficient. Sometimes they are lucky and the pursuer is lucky. But let's see what happens when the pursuer really learns something. It learns basically two strategies. It learns either to mirror somehow the pursuer are always in red, sorry, and the evader in blue. To mimic, to mirror the trajectory of the evader, or somehow to follow it. This is more clear from this movie. You see, he is performing a tailgating, and this movie shows also something interesting. You can have a switch between the two strategies, tailgating and mirroring, upon a close encounter between the two, which does not lead to capture. Interesting, these two mirroring and tailgating strategies can be somehow interpreted. We were able to understand a bit how they are linked to the information the agent gathers. Essentially, what the pursuer learns is to maintain constant the combination of angle he receives. And essentially, mirroring corresponds when this angle is equal to pi, and tailgating when this angle is equal to 0, which can be also rephrased in terms of the bearing angles that I introduced before, like being their sum to be 0 or to pi. And this is shown here. And you see that the change from pi, which is tailgating, to mirroring, which is 0, happen actually in this precise moment when the evader is close to the pursuer. Notice that due to the symmetry, the two strategies cannot be really distinguished. So it's really a matter of initial condition which determine which strategy is taken. If you neglect the hydrodynamics, you can write from the equation of motion without the hydrodynamic part, the equation which the kinematics of the problem, and you can derive equations for the distance and for the bearing angle. And imposing these constraints, which we understood to be crucial for these strategies, you can derive these two equations, which rule the distance and the bearing angle. And we can see that the consequences of this is very clear when the velocity are equal. When the velocity are equal, you see that the bearing angle of the evader is a random variable because it plays a random strategy. And the distance is just performing a random walk. So essentially, you commuted the random walk in 2 dimensions, the random search in 2 dimensions, and random search in 1 dimension. This is in the perspective of the predator. And the evader is simply performing a random walk till it touch, if it does in the proper time. Conversely, of course, for different velocity, the axis of symmetry is not precise, and you are not on a line, but anyway in a reduced manifold. In the tailgating, instead, if the velocity are equal, you are trapped because this guy is 0, and so the distance is constant. While if it is different, you helped by the dynamics of the bearing angle. This is a vectorial representation of this equation, which led the pursuer to go at the back of the pursuer and capture it, or the evader and capture it. Now we see the counter strategies discovered by the evader in his learning term. The first one is very interesting. He is completely able to exploit hydrodynamic. So essentially, this is probably when he received tailgating from behind. He is able to put himself in a position with respect to the pursuer, such that the hydrodynamic field cancels the velocity advantage of the pursuer, which is slightly faster than the evader. This is the movie is in the perspective of the frame of reference of the evader. The other strategy it learns is to do linear escapes, possibly to fastly go away from the evader, but somehow built in the mirroring, because now the pursuer is not learning. There is the possibility to do these capture arcs to reach the evader at a rendezvous points, which sometimes fails, like here, and sometimes, like shown in the movie, it works. The idea is that the mirroring is happening by slightly changing the axis of symmetry from time to time, and this allows the predator to catch his prey. In the later learning cycles, also interesting things happen. So, for example, you can see here pursuer learn to evade from the hydrodynamic defense, to escape from it. Later on, the evader learn to do this turn, which trap in twirling motion the pursuer. Sometimes it doesn't work. And very interestingly, what's happening here. Essentially, this run, which is the run in which the evader win most of the time, what the evader learn is to make some turns at distance, which make the pursuer to exchange its strategy more or less from mirroring and tailgating, but at a distance such that is never able to really to come closer to its prey. So essentially, in this way, the evader is able to maintain itself at distance from its predator. And this is very much represented in this random realization of the learning process. So I come to a conclusion. Essentially, we see this work more or less mostly as a proof of concept to see that using reinforced learning methods, one can somehow rationalize predator-prey interactions, also in conditions of partial information, as you can have in a situation like when you have only hydrodynamic cues. This can lead, for example, to some inspiration for rationalizing also other kind of animal behaviors. And as a perspective, I mean, there are many interesting things which can be done. I mean, to increase the realism, like adding multisensual signals, including external field, external flows, or very interesting is to consider many prey and many predators and see if using multi-agent reinforced learning, collective search and escape strategies can emerge. So with this, I thank you, and I will tell you that I will miss a lot of the tortellini tonight. Thank you.
Thank you, Massimo. I think we are really very short in time. If there is anybody who wants to raise a question from Massimo, please do it now freely, because in principle you should use the chat or raise your hand, but it's easier to listen for the question immediately.
Ciao Massimo, I'm Francesco. I have a very short questions, if I may. You mentioned as a possible application considering collective hunting strategies. Do you think that to have them become interesting, you should ingrain some kind of heterogeneity in this kind of model? So in a sense, force the agent to develop different behaviors, or it can emerge spontaneously, this kind of... I'm thinking of strategy where part of the group pursues and another part sets up a trap or something like that.
I see. I don't know if you really need some heterogeneity. I can tell you, for example, there is this nice work on hydrodynamic cloaking. In this case, if I remember well, they did some sort of heterogeneity. So there you have a sort of like three swimmers. And the idea is that the two swimmers want to hide the third one. So they need to organize their motion such to, if I remember well, to make that situation such that at distance the third one is not seen. But I'm not completely sure that you really need heterogeneity. I mean,
so you can develop.
I mean, eventually you can even. I mean, first of all, heterogeneity can emerge spontaneously. For example, I think in the sense that if you let them to choose their own strategy, maybe they discover that they have not to adopt all the same strategy, but one should be, I don't know, the defender and the other the defended, or something like that. Or maybe there could be something which can be realized without heterogeneity. It's a nice question, but I have no precise. I mean, one should try and think a bit.
I'm sorry to interrupt you, but we are really out of time.
Sure,
I think that we can go on discussing privately.
Sure.
And since we are really short in time, please, we should pass to the next.
Okay. Thanks and goodbye.
Should I share?
I stop sharing.
Afternoon session, and Paolo de Los Rios is going to speak about the non-equilibrium nature of thermophoresis. And
Yes.
please, Paolo.
Let's see. Okay, and I think, do you? Oops. Do you see the presenter mode, or do you see the?
Well, it's more or less okay, but it's not full screen, but it's okay. I think everybody.
Do you by chance see the presenter mode? Or
You see the presenter mode.
You see the presenter mode?
Yes.
Okay, so let's do it otherwise. So let's do just, sorry. The old way, and it should be like this. No, I cannot find. Of course, every time Zoom will work in a different way. Still presenter mode? Hello?
Yes, okay, we can see it.
No, but I'm going to make it. I'm sorry.
I know that it's not deterministic the way it works.
It always works, of course. This time it doesn't. Let's do like this directly. Okay, and I don't know why it refuses not to show the presenter mode.
Maybe you say something there's on the left, something use slideshow. Maybe that is a magic solution. Huh?
Here.
Yeah, where you see on the upper left, yeah, there's something use slideshow. Maybe that does it for you.
Or swap displays.
Yeah.
Ah, maybe.
Yeah.
Well, let's do like this. Wait, this will make it easier.
Okay, try, yeah.
Just instead of using two screens, I'm going to use just one, and this time it should work by definition. Now my mouse doesn't work anymore. I'm really sorry. I didn't expect all of this.
Do it this way. I mean, it's okay. No, it's okay.
Is it okay now?
Yeah.
Okay. Perfect. Sorry for the inconvenience. So, do you see also my mouse here?
Yes, we do see it.
Okay, thanks. So I'm sorry. So what I'm going to, first of all, thanks the organizers. It's a real pity that we cannot be all in person for the for tonight, for actually tomorrow night, and to meet all together. But thanks again for the opportunity. What I'm going to tell you now is something that we stumbled upon almost by chance, that we didn't expect to be talking about thermophoresis. Actually, that was not our goal initially. And actually, it was related to more no-equilibrium work that we were doing. But let me just start from a short primer about thermophoresis. So thermophoresis actually has been discovered quite some time ago. We're talking about 170 years by Carl Ludwig, and has to do with the fact that if you impose on a solution of molecules or particles a thermal gradient, you will see an accumulation of particles on one of the two sides. Typically on the cold side, and that could be almost intuitive because you can think that on the cold side particles will diffuse less, and so they will not go away. On the warm side, they will diffuse faster, and so they will go away, ending up with an accumulation on the cold side. But actually, it turns out that there are cases, and not so few, where you see the opposite, an accumulation on the warm side. And this is, of course, less intuitive. And because of this, people started being interested in some understanding what was the root cause of this phenomenon. And the problem is that this phenomenon occurs on very different systems. It applies to from the 1 nanometer, let's say a few nanometers range, to the micrometer range. So
2 orders of magnitude at least 2 orders of magnitude in length, even more. It applies to solutes that can be polar and non-polar, to solids that can be polar and non-polar. So there are so many different systems, both in scales and non-macroscopic features, that people have tried to develop a theory in time, but actually there is no success in having a definitive answer of the causes of thermophoresis. So I just highlight here 4 of them. Of course, there are many more. Some of them, like the first and the last ones in this list, tend to give more emphasis to the hydrodynamics of the particles, and this applies to larger particles. Others, like the second and third, tend to give emphasis to the to the ionic properties of the particle and of the fluid, which of course means that they wouldn't apply to non-polar particles or non-polar fluids. So to summarize this part, the fact is that there is no comprehensive theory. There might not even be a comprehensive theory. Maybe what we observe is the sum of many different effects, all of them obeying some sort of thermophoretic contribution, or giving a thermophoretic contribution, but there is not a single one that you can make out, and that's of course a possibility. What people have done anyway phenomenologically to deal with thermophoresis essentially has been to deal with it just thinking at steady state, looking at the distribution of particles at steady state, thinking that you should write the usual time derivative of the current, which then of the concentration, that of course goes to 0, and you are left with a current, which is the usual 2 terms. So first of all, there is the usual diffusion term, the gradient proportional to the gradient of the concentration, and then there is a drift term proportional to the concentration itself and to a force, and the force has been postulated to be proportional to the thermal gradient through a thermodiffusion constant. Now, of course, if you impose, thinking about closed boundaries, that this current must be 0 everywhere at steady state, then you end up with a simple solution that is governed by a coefficient, which is the Soré coefficient, which is nothing else than the ratio between the thermodiffusion constant and the diffusion constant. And here I stress that both these parameters are not derived from microscopic properties, are measured. Now, of course, for the diffusion constant, we know a little bit more. For the thermodiffusion constant, essentially, is something that comes out of the experiments. And the sign of the Soré coefficient, as you can see from the solution, will decide where the accumulation takes place. So if it is positive, particles accumulate on the cold side. If it is negative, they will accumulate on the warm side. So that's what we know phenomenologically. But as I say, there is no theory, comprehensive theory. It's not to say that there haven't been progresses. There have been quite substantial advances. But as I said, more related to hydrodynamics or more related to charged particles on the microscopic scale. And actually, what we were doing that led us to thermophoresis was that we were studying actually, and this is reported in this paper that just appeared, we were interested in systems, multi-state systems that have multiple internal states, if you want, and they can diffuse, let's say, in one dimension, but in the presence of a thermal gradient. And we were more interested in what happens to the distribution of molecules, or let's say of particles across the different states over space when there is a thermal gradient. And actually, we didn't immediately realize that there was something that looks like thermophoresis, as I will show, because for simplicity, we had chosen always the same diffusion constant for all the particles, for all the states, sorry. Also, for simplicity, we are assuming here that the diffusion constant doesn't depend on the position. But for such a system, n-state system, that can diffuse and can transition from one to another different internal states, we can write down the usual diffusion equation. So the time derivative of the probability of being in one state, the diffusive part, and the transitions from one state to the other. And now the dependence of the temperatures, the thermal gradient, comes into play here in these transitions, because we assume that these transitions, let's say they are Arrhenius-like. So, for example, between state 1 and 2, the ratio between the two rates will obey the usual Arrhenius law. Now, of course, the absolute velocity will depend on the barriers that you can have in between. But also we have to remember what people look at when they measure thermophoresis. They just look by, for example, optical means, could be turbidity, could be refraction index, could be fluorescence or whatnot. They look at the total amount of molecules in different regions of the system. So essentially what we have to do is to sum up all these equations, so getting the time derivative of the total probability, and of course locally all the transitions will cancel out, and what you obtain is something of this form. So you have, if you want, the divergence of the gradient of the sum of all these terms, and this is your minus total of the current. And of course you are not solve the problem easily, because you still have to determine all the PI, all the probabilities of the individual states. Now, and of course, there are n equations. So let me show you what happens from if we focus on just two states for simplicity. Now, if you just work on two states, I will come back to the detail, well, not too many details, but just to the idea of the solution. If you just focus on the steady state, at the end, the solution to that equation has to obey at steady state this relation. So it's the gradient, so the total current, apart from the minus sign, is the gradient of this term, which looks very much like the usual diffusive term, so the diffusion constant, but in this case is the thermodynamic average of the diffusion constants, just what you would take using the probabilities of the individual states. But of course, this depends on space, because T depends on space, temperature depends on space. And an extra term, which is given by the product of the diffusion constants of the two states divided by essentially the velocity of the reactions, of the transitions, and the second derivative of the probability distribution itself. If the probability distribution changes slowly, already this term will be small. If on top we assume that reactions are faster than transport, then we can, to a first approximation, neglect this term. If we do neglect this term, and I stress this equation is exact in its derivation, if we do neglect this term, we are left with just the gradient of this parenthesis. And if we go back and we now look back at what we had for thermophoresis, the phenomenology was given telling us that the current was, as we wrote before, now I use the probability instead of the concentration, but of course they are the same thing. We had this relation, and this was the Sorey coefficient. Now, looking at the, let me call it principle, just because it's a series of steps where there are no major assumptions, and we start from a microscopic description of this toy model. What we obtain is just that, looking at the correspondence, we can apply the gradient to the different parts. We obtain a Sorey coefficient in this case, which is given by the derivative with respect to temperature of the diffusion, the equilibrium average of the diffusion constant divided by the diffusion constant. So in this sense, what we found, as I said, we didn't expect, because we used initially all the same diffusion constant for all the states, and then at some point say, let's relax this hypothesis and let's see what happens. And we realized that actually that was the first outcome, that there was thermophoresis, so the particles were accumulating on one side. And it depends on the fact that there are different diffusion constants. So let me say different transport properties for the different internal states of the system. Because of course, if they were all the same, this equilibrium average would not be an average, would be an exact value, and the thermal derivative would be equal to 0. So the fact that there are different transport properties for the different states is the key for the appearance of thermophoresis in our model. Actually, what I glossed over before, actually I said it, that of course this is one equation. We know that actually there are many equations. For example, there will be 2 equations for a 2-state system. And actually, you have to write down also the equation for the second the equivalent for the second equation. For example, you could take the difference of the 2 probabilities or any linear combination that is independent from the sum. And if you take just the difference, just for the sake of it, what you discover is that it obeys an equation which is not a continuity equation. So there are sources and sinks. And actually, this tells that there are currents in the system. So this is a genuinely non-equilibrium phenomenon. And indeed, actually, this is not difficult to understand. On the cold side, you will, from the cold side to the warm side, you will have a net flux of molecules, the low energy molecules, going from the cold to the warm side. And high energy molecules will be excited, or states will be excited on the warm side and will move. There will be a net current going to the cold side. Of course, the sum of the 2 currents in any section is exactly equal to 0, so the total probability is currentless. But of course, there will be these cycles, which is necessary, by the way, to transport heat, because we have a thermal gradient, and thermodynamics tells us that we need to transport heat. So this is consistent with thermodynamics, and actually there are space and internal currents. And actually, what I said before also is that I was choosing, or we were choosing this diffusion coefficient to be independent of space. Now, we know that in principle, if you apply Einstein's relation, it should be kBT over gamma. T depends on space. And actually, there is a way to obtain this result, which is well known. You start from Cramer's equation, you go to the underdamped limit. So large values of, overdamped limits, so large values of gamma. And you can derive just the spatial part of the equation, which is the usual diffusion equation. And now, instead of having the average of the diffusion constant over the internal space, you have the average of the square of the velocity, which by Einstein's relation turns out to give exactly the same form that we had before. But if you think of it in terms of velocity now being the transport property of the different internal states. Now, the different internal states are the different velocities. So each velocity represents an internal state for the particle. You can then associate this as a sort of an average of the transport properties, the thermodynamic average, because it's taken according to the local Maxwell-Boltzmann distribution. And okay, you can compute, if you want, a sort of a Soré coefficient in this case. But what is interesting to us, was to realize that actually also in this case, which is particles without any internal states in principle, or you can also consider it even if there were internal states, and so you would have a superposition of the 2 effects. Warm particles, so high energy particles there is a net flux of high energy particles, of fast particles going from the hot to the cold side, releasing heat. And there is a net flux of particles from the cold to the hot side, so slow particles from the cold to the warm side. Once again, the sum of these currents in space, for any section is equal to 0. So the system appears to be currentless, but actually inside there are continuous currents between space and real space and the internal space. And so this applies to both situations. Now, if you want, I'm just coming immediately to the conclusions. I went actually faster than I expected. The main message for us, as I say, we stumbled upon this almost by chance, and then we were looking at thermophoresis, and we never saw any kind of result looking in this way, in this way. So what happens is that thermophoresis emerges when particles have several internal states. There could be chemical spaces, conformations, velocities, and essentially that have different transport properties. And there is this interesting interplay between transport and the internal average of the diffusion constant that gives rise to this, this curious effect. And actually, we don't know whether this could be a step toward a general theory of thermophoresis. Very likely not, but could be an interesting effect to be taken into account, because ultimately, when we think about molecules in a liquid, what precisely are all these internal states also is a little bit vague. It's not just conformations, it could be the different states of the hydration shell, if you want. Or when we think about screen, Poisson-Boltzmann or the Bayukel screening, actually this is a sort of a mean field average description of how the ions accommodated around a charged particles. Of course, by fluctuations, there are all possible other screenings, naked particles, over screen, and so on. And they might have different transport properties because they will bring together or bring with themselves around different hydration shells, different amount of charges, and so on. So there might be something to take into account there. And just to conclude, okay. And just to conclude, so there is this sort of very interesting, as I say, the interplay between internal states and transport. And we are wondering whether we could have give a little contribution. Of course, that would be the dream, but at least a contribution to the field of thermophoresis just by this tangential direction that we came from. And maybe it could help developing a more comprehensive theory. Then let me thank my collaborators, Daniel and Shilin, who really did the heavy lifting for this work, the Swiss National Science Foundation for support. And here are the references. So the thermophoresis paper is on the archive. The other one that was sort of the inspiration has already been published. And with this, I thank you. I stop the screen sharing, and I'm eager to listen to your questions.
Thank you, Paolo. Very interesting talk. If there are questions, please, you are kindly invited to pose the questions immediately, as soon as possible, because they are really out of time.
Yes, so Paolo, if I might ask a quick question.
Sure.
So clearly, I mean, it is more or less clear if you're, macromolecules and so on and so forth. But if you take a simple colloid, I mean, there is not much beyond electrostatics well, you might have some surface properties. And then in this simple case, which could be the internal states? It has to do with electrostatics only? Because as far as I know, you can get also positive or negative values of the Sorey coefficient with simple particles. So that is highly unclear why.
That's a good question. We are looking at the literature right now, which is, as I said, really vast. And it's interesting that, first of all, as soon as you go to larger particles, of course, you cannot exclude the hydrodynamic effects and so on. But what is interesting is that oftentimes they try to rederive the results in terms of surface tension, so variation of the surface tension with temperature. And in a way, if you think about the surface tension is a free energy, and as a free energy is a sort of takes into account also all the possible ways the fluid at the boundary with the particle is exploring its different states. Whether this has anything to do with what we are seeing in our toy model or not, that's something that we would like to explore more. But is a sort of a thorny field, to be honest. It's not that after 170 years and people banging their head on the wall to get a solution, there are camps, there are well-rooted ideas, many good ideas actually, of course, that you should never disregard. Many different effects. As I said, I'm not so sure. I actually think that what we observe is a sum of many different contributions that at different scales depend on different principles. That's perfectly well be.
Okay, thank you.
Are there any other questions? So if there are no other questions, I would have one, but I'll make it privately to Paolo. And I think that we can stop this afternoon session and go to the coffee break before the Ignite talks are going to start again at 16:10, as far as I know, as I remember. Fine. Thank you very much to all the speakers of this afternoon session. Paolo, if you're still there, since I skipped my coffee, I want to ask you. But so in general, the structure of your model, which is very interesting, is also very complicated in principle, because if you really need to take into account specific features of changing diffusive properties of particles inside a many particle system, that will lead to some strange behavior. Maybe you can expect very unexpected, you can at least wait for very unexpected configurations that probably have nothing to do with thermophoresis in the general sense that you have something clustered somewhere on one side or the other. Maybe you could really manipulate, according to the thermal gradient, different distribution of particles in space. In some sense, that should be solved self-consistently. It recalls me, there is a strange analogy with what Herbert was speaking before. I cannot explain to you why, but there is, believe me. So
I do. I absolutely do. No, first of all, the formula that we have, that is for the Sorre coefficient, that there is the derivative with respect to temperature of the diffusion constant. If you take the derivative of this average, actually what you obtain is nothing else than the correlation, technically the covariance, if you want, of the energy and of the diffusion constant. So essentially, if you take particles that become faster, have a higher diffusion as they get higher in energy, you will have, so that would be positive, and it will accumulate on the cold side. If there is an anti-correlation, then they would accumulate. So we have a sort of explanation. Then if you look at the distribution of the different states, although the total distribution might be skewed on one side, also the individual states are completely skewed in many different ways. So it's and so you could find concentrations that are not even necessarily monotonic, because they could start tilting in one direction, but because of other reasons, just the way they are filled in this pseudo-equilibrium, they are depleted in one region. So the two effects could go against, and you might have bumps. So if you just look at the internal distributions, they might be quite complex. And of course, not in the case of two states.
Yes,
but
it's like a sort of self-consistent coupled transport problem, because you have different parameters entering the game, and you can really, in principle, I think, manipulate the situation in such a way that it may appear very
absolutely, no, absolutely. In principle, one could try to do some sort of fit of the diffusion equation for a certain pattern that you would like to have, letting it find a minimum number of states that is necessary to get this sort of pattern. Yeah. Whether this is realizable, that's a completely different issue.
No, that's another story.
Out of a computer.
With the toy model, at least it would be a really great improvement. I mean, it's very interesting, very, very interesting.
But as I said, it was actually kind of by chance, because we were working on the other system where we, to emphasize other effects, we were taking all the diffusion constant equal, just not to superpose different effects. And then I say, okay, now let's take different diffusion coefficients and thermophoresis. Well, thermophoresis. It is thermophoresis as far as it has the same features of thermophoresis. That whether it has anything to do with real thermophoresis, that's a different issue.
Okay, well,
but
it's a nice step. It's a really nice step. Thank you very much.
Thank you.
By the way, so we see at 16:10, but in 3 minutes, I think.
3 minutes. I will run, grab a coffee, and I'll be back.
Yeah.
Ciao Ginestra.
Ciao.
Piacere vederti. Tutto bene?
Sì, sì, tutto bene. Quindi 5 minuti incluse, incluse domande? Mhm.
Yeah.
Bene.
Ci vediamo fra poco.
Sì.
Un'impresa difficile.
No, no, Ginestra lo può fare
Dire
benissimo.
un'impresa difficile, t'ha messo
Ginestra lo può fare
una bella impresa.
benissimo.
So che è brava adesso.
Abbiamo il coffee break dopo, no?
Sì, sì, sì. Ok.
C'è il primo speaker?
Sì, ci sono.
Vuoi intanto
Sì,
condividere?
posso, aspetta. Ecco, ma c'è anche il video.
It's a real pleasure to chair this session of Ignite Talk. So this is good for me to be virtually in Parma, although we all miss the tortellini. And each of you have 5 minutes for the talk, including questions. So we are already running 1 minute late.
Yeah.
So the first speaker is Lorenzo Buffoni. Okay, to you.
Yeah. Yeah, thank you. Thank you for having me. Do you see my slides? Correct?
Yes,
Yeah, okay, nice. So before I start, I want to acknowledge the mentorship of Michele Campisi, which has been my supervisor during these works that I'm going to present here. And so, as the title implies, let's jump straight into quantum annealing. Before starting with the thermodynamics part, I wanted to briefly introduce quantum annealing. So in quantum annealing, we can think about having a lattice of qubits or quantum spins, which can be evolved with an Hamiltonian, which is composed of 2 terms, a classical terms, which has only sigma z spins and sigma z interaction, and a quantum term, which has a transverse field over the x direction. And this Hamiltonian can be governed by a parameter S, which is called the schedule in quantum annealing, which can be varied between 0, so the Hamiltonian is completely quantum, and 1, and the Hamiltonian is completely classical. That allows us to perform some particular types of schedules called reverse annealing protocols, in which we start from the classical Hamiltonian. So we start from a classical configuration of spins that we can choose. We can initialize the system as we want. Then we turn off the annealing parameter, which means that we turn on the transverse field, the quantum part, and then we turn the quantum part off and we read out the result. From a thermodynamical perspective, this allows us to think about the quantum annealer, in our case the D-Wave 2000Q, as a thermal machine, because we can initialize the system in a classical state. We can sample this classical state according to a certain probability distribution, and we can fake that the system is in contact with a hot thermal bath. Then we can drive the system doing that turning on and off the transverse field, so the quantum part. And then naturally, since this is an open quantum system and it physically sits inside a dilution refrigerator, this evolves in contact with an environment which is around 15 millikelvin. So it's inside the dilution refrigerator, which is colder typically at the temperature at which we initialize the system. So this thermodynamical picture of the quantum annealer allows us to do a thermodynamical analysis and ask ourselves the question, how does this cheap quantum computer operates from a thermodynamical perspective? So does it behave as a refrigerator, so transferring heat from the cold bath to the hot one by an external input? Does it work as an engine, as an heater, or as a thermal accelerator? To know that, we want to be able to measure various thermodynamical quantities. So ideally all the energy exchanges happening between the various parts of the thermodynamical system. So the various heat baths and the work input that we put into the machine, as well as the exact temperatures of the 2 baths. Of course, this is not possible because we don't have full control of the system. And furthermore, we don't own the experiment. So this thing is sitting in a lab in Canada, owned by D-Wave, and we are just accessing these through the cloud. So we can really only measure this delta E1, but using some clever thermodynamics, which I don't have time to explain, we can lower bound these other quantities. And so basically we can infer from the lower bounds of these thermodynamical quantities the regimes at which the quantum annealer is operating. In our case, we can see that if we initialize the system with an initial state with an infinite temperature, we have that the initial state has zero mean energy. And if we let the system evolve without driving, we see that we have a slow heat loss due to the coupling with the cold environment of the fridge as the time increases. If then we fix the time at like 100 microseconds, which we can see corresponds to a dissipation of 0.25 of energy, this corresponds to this point here. And at this point, we can turn on the driving, so turn on the transverse field, the quantum driving, and we can observe the change in energy as we turn the driving on. And the more driving that we put into the system, so 0 would be going from classical all the way to quantum and then all the way back to classical in terms of the driving Hamiltonian, we see that we dissipate like almost instantaneously to near the ground state, which is -2 in this case. So we have a really, really fast heat loss into the environment, adding this driving. That means, from a thermodynamical perspective, that that this thing is behaving as a thermal accelerator. And the results of like all the analysis is contained in this work. And I'll jump these other slides that I don't have time to show in 5 minutes. But the idea, the conclusion that I wanted to tell is that we can use quantum annealers, or in general NISQ devices, so noise intermediate scale quantum devices, as fully fledged experiments. And this device can be analyzed as thermodynamical machines. We can use them as really experiments to validate theory, and they have the advantage that they are easily accessible, so you don't have to own the lab to perform the experiment, and replicable. So you can just write the code, and for example, we share the code to replicate the experiments on GitHub. And yeah, so that's it. You can find the details in these 2 papers, which I've cited here, and you can contact me at the email. Thank you.
Okay, thank you so much. A lot of virtual clap. I think we are kind of running a little bit late. I don't know if the other next speaker, which is Ashwin Gopal, wants to set up the slide.
Yeah, can you hear me?
Yes.
And you can see the slides, right?
Yes, thank you.
Okay, good afternoon, everyone. Thank you for the organizers for inviting me. Today, I'll be talking about stochastic energetics of critical oscillators in active baths. This work is done in collaboration with Edgar Roldan and Stefano Ruffo. Sorry, I cannot move the slides. Yeah. So active matter has been a field of interest, particular interest, due to its non-equilibrium nature, as the individual agents consume fuel from the environment and produce some mechanical output. And there have been many interesting phenomenologies due to this non-equilibrium nature. But one interesting phenomenology is called activity rectification, where the systems can extract useful work out of the non-equilibrium nature of the bath or the activity. So to explore this idea, we studied a toy model of Adler oscillator in the presence of active baths, and we modeled this as a overdamped Langevin dynamics of a Brownian particle in a tilted washboard potential, and where the tilt is controlled by the non-conservative force F, and the active noise is modeled as a noise with exponentially correlated memory, and with a memory time correlation time tau. And as you can see, as the correlation time goes to 0, we get back the thermal bath limit. And one interesting feature is that when you take the correlation time to infinity, you get back the deterministic limit. Even though this model is particularly simple, this is a model used to study intracellular transport. It's a model for Josephson junction, and also has been recently studied for studying phase locking in hair bundles. So to study the thermodynamics, we use the tools of stochastic thermodynamics to get the statistics of thermodynamic quantities at the trajectory level. We can define the thermodynamic quantities, and the quantity of interest is work done on the system, which is just integrated current scaled by the non-conservative force. This model is particularly interesting because of the nonlinear nature and due to the bifurcation behavior at the deterministic case. So this system shows a saddle node bifurcation at f equal to k, which means that below f, when f is less than k, the system goes to a fixed point. Whereas when f is greater than k, the system just keeps on oscillating. So in the case of thermal bath, in the thermal bath limit, we derive exact expressions for the average power inputted into the system. And we see that with increasing temperature, the average power increases in the system. And what we found interesting was that at the critical point, usually in deterministic cases, you have these scaling behaviors in nonlinear systems, and we could extend such scaling behaviors in the presence of the thermal bath also. And we could find an exact scaling behavior at the critical point. And in the presence of active bath, what happens is that, as we expected, the system goes from thermal bath limit to the deterministic limit as you increase the correlation time. But we could also show that at the critical point, there is a different scaling behavior than that of the thermal bath limit. Now, even though the behavior seems to be as such going from a thermal bath limit to a deterministic limit, we find that there are different behaviors below and above the bifurcation point. And as you can see, above the bifurcation point, there exists a finite correlation time where the power is minimized in the system. And to study this analytically, one has to deal with approximation schemes, as this is a non-Markovian system, non-linear non-Markovian system. And there are many, there are two famous approximations called Fox approximation and UCNA, which are used to study these equilibrium systems in the presence of active baths at small correlation times. But we can see that both these approximations cannot capture the non-monotonous behavior in the average power. And we see that the Fox approximation works until the angular velocity distribution is close to Gaussian. And
so you can wrap it up a little bit. Yeah. So
we also derived the exact expression for the average power at the large correlation time limit. And regarding fluctuations, we derived the exact expression in the thermal bath limit, where the diffusive behavior is enhanced at the critical point. But in the presence of active bath, we found that the diffusive behavior is further enhanced. And to wrap it up, we also looked at the uncertainty relation, and we found that there is a uncertainty relation, finite time uncertainty relation for such systems, for such active systems. And we found that you can go below the thermal bath limit bound. So these are the conclusions, and we see that there are the presence of the correlations produce significant measurable signatures in the work exerted on such systems. So for further details, you can find in this article. And thank you very much for your attention.
Thank you so much. Yes, so you are taking a lot of time. I don't know if there are any questions, but I will suggest the next speaker to set up for the next talk. Okay, so the next speaker is Samantha Kundu. Perfect. Yes, we see your slide. But you appear to be muted if you are speaking.
Now, is it fine?
Yes, yes.
Okay, thanks. Okay, good afternoon, everyone. I'm Sumanta Kundu, a postdoctoral researcher at the University of Padova. I'm going to talk about breakdown of universality in random sequential adsorption in the presence of spatially long-range correlated disorder. Okay, so the phenomenon of adsorption deals with the attachment of particles onto a surface, and in the simplest case, in the statistical physics, the model which captures the essential features of the phenomenon of adsorption is called the random sequential adsorption. And in the simplest case of monolayer formation, the particles in the form of dimers, which occupies 2 consecutive lattice sites, are deposited one by one and adsorbed irreversibly at random locations, with the only constraint that they cannot overlap with each other. With this, the dynamics is continued until a jamming state is reached, where there are no more vacant space available to adsorb a single particle. So at this stage, there exists some vacant space, but those vacant spaces are smaller. So the size of those vacant spaces are smaller than the size of the particles, and it attains a non-trivial value at the jamming state. The surface coverage has a value of this 0.8646, which is known exactly in 1 dimension, and in 2 dimension, it is known up to the numerical accuracy 9068. In our case, we have introduced defects into the system, which exhibits spatial correlation, long-range spatial correlation, and the correlation function decays in this fashion as a power law with the distance, and gamma determines the strength of the correlation. For small gamma, the defect space is highly correlated, and with increasing gamma, the spatial correlation is decreased. And we tune the value of gamma and study how the spatial correlation affects the percolation and jamming transitions in random sequential adsorption. Well, this is the configuration at the jamming state. These red sites are the defective sites, and blue sites are the sites which contains particles. So we characterize the jamming transition and it is characterized in this way: fluctuation of the jamming density, and usually it is characterized by this way. And this is the size scaling of the fluctuation of the jamming density. It scales in this fashion. Usually B is 0, and the exponent nu j varies as 2 by d. D is the spatial dimensionality, and it holds both for pure system without defects and for uncorrelated system, in both cases. And it is irrespective, it holds irrespective of the lattice geometry, size, and size of the particles, shape and size of the particles. But as you can see here, as we increase the correlation strength gamma, we tune the value of gamma, and we have seen that the correlation length exponent, which characterizes the jamming transition, it varies systematically with the strength of the correlation. So as you can see, for very small defect density is sufficient to change the universal behavior of the jamming transition. Now we study the percolation transition as well. So for a given defect density Q, we tune the value of Q and wait until the system reaches a jamming state, and ask the question whether the jamming configuration is a percolating one or non-percolating one. So as you can see, as we vary the defect density, the percolation probability decreases, and this is for 3 system sizes, and this is the finite size scaling. For gamma is equal to 0.8, and this exponent nu p that characterizes the correlation length exponent of the percolation transition. And in case of gamma is equal to 1.5, it is completely different. And here you can see that as we tune the value of the correlation strength exponent, the correlation strength gamma, the value of the percolation correlation length exponent, that changes systematically with the strength of the correlation. And for gamma tends to infinity, that is the case of uncorrelated defects. As you can see, it approaches towards the universal value, which is exactly known in 2 dimensional, that is 3 by 4, 0.75. So that was the case for percolation through the percolation at the jamming state, but we can also study the percolation before the jamming state.
Wrap it up. Yeah.
And you can see as we increase the value of P, for small defect density, we can see the non-universal behavior of the percolation transition. And we have seen that for uncorrelated defects, actually in case of percolation, the largest cluster of void space is important. But for we have investigated that for uncorrelated defects, the scaling is like this. But for correlated defects, it is like this, which might be the possible reason for breaking the universality class of percolation transition. But the precise reason for this non-universal behavior is still under investigation. And to conclude, we have investigated the percolation and jamming transition in the presence of spatially correlated defects, and we have seen that the correlated disorder has profound effect on the jamming and percolation transitions. Specifically, the universality class of the jamming and percolation transition is completely broken when we introduce spatial correlation. And the deviation of the correlation critical exponent values, the non-universal behavior of the transitions are very pronounced in the case of strong correlated disorder. Okay, thank you for your attention.
Thank you so much. We continue this kind of marathon with the next Ignite talk. Giordano De Marzo, if you want to set up your slide.
Yes. Can you see them?
Yes.
Okay, perfect. Good afternoon to everybody. I'm Giordano De Marzo, a PhD student at Sapienza University and Enrico Fermi Research Center. And in this short talk, I'll briefly show you the main ideas behind the paper Dynamical Approach to Zip Flow, written in collaboration with Andrea Gabriele, Andrea Zaccaria, and Luciano Petronero. First, let us consider a system composed of n objects with power law distributed sides, so that the probability of observing an object with size S is a power law with exponent minus alpha. I denote by S min and S max the lower and upper cutoff of this distribution corresponding to physical intrinsic limit always present in real systems. If we order the objects from the largest to the smallest, and we denote by S of k the sides of the kth largest one, we obtain the so-called rank size relation of the system. This relation, on the left, is of the same form of Zipf-Mandelbrot law, and this allows to derive three relations connecting the three parameters of Zipf-Mandelbrot law to the parameters of the inherent power law distribution and to the number of elements in the system n. Note that for the parameter q going to 0, Zipf-Mandelbrot law reduces to a simple power law scaling, and so we recover the well-known Zipf law, which has been observed in a variety of systems ranging from cities and language to lunar craters and earthquakes. For this reason, Q quantifies the level of deviation from Zipf law, since the larger is Q, the more severe are deviation from a pure Zipf scaling. Moreover, from the expression of Q, it is also clear that the deviation parameter Q is related to the level of sampling of the inherent distribution, since this parameter is the smaller, the wider is the extension of the power law, and is the larger, the greater is the number of elements in the system. Now, most complex systems where Zipf law is observed are in continuous evolution. And as a consequence, both the number of elements in the system and the parameters of the power law vary with time. Since the deviation parameter Q is a function of these quantities, it is natural to investigate whether or not Zipf law is dynamically stable, and so if Zipf law is an attractor of the dynamics. In order to do so, we introduce the temporal variable small n, defined as the total size of the system, and we can face two situations. First, the derivative of the deviation parameter Q with respect to small n may be smaller or equal to 0. In this case, Zipf law is dynamically stable, and so we say that the system shows Zipfian dynamics. Conversely, if the derivative of Q with respect to small n is larger than 0, the dynamics makes deviation from Zipf law increase, and so Zipf law can be observed only temporarily. For this reason, we say that the system shows a spurious Zipf law. Note that these two classes of systems, those showing Zipfian dynamic and spurious Zipfian systems, are characterized by different statistical properties. Indeed, recalling that Q quantifies also the level of sampling of the nearest distribution, we see that while Zipfian dynamics drives the system toward an undersampled configuration, system showing a spurious zip flow evolving completely sampled the inherent power law distribution. In the figure, I plotted the behavior of Q with respect to N for different system N models. Red curves correspond to spurious Zipfian systems, such as world cities and earthquakes, while blue curves are indicative of a system characterized by Zipfian dynamics, such as US cities and natural language. Concluding, the take-home messages of this short talk are three. First, the flow cannot be studied by considering fixed time snapshots of systems, but instead it should be analyzed by studying the dynamical evolution of systems. Second, by looking at the dynamics, it is clear that Zipfian systems are divided in two distinct classes characterized by different properties: spurious Zipfian system and system characterized by Zipfian dynamics. Third and last, since most studies about zip flow are performed statically, they are unable to distinguish between spurious zip flow and Zipfian dynamics. As a consequence, they claim the ubiquity of zip flow may be mostly a spurious phenomenon. Finally, for those interested in this topic, more details and analysis may be found in the paper Dynamical Approach to Zip Flow, but also in the work Zip Flow for Cosmic Structures, How Large Are the Greatest Structures in the Universe, already published, and in Quantifying the Unexpected, a scientific approach to black swans that is in preparation and will be available on arXiv soon. And so, thanks you for your attention, and thanks to Andrea Gabrielli, Andrea Zaccaria, and Luciano Piedronero, and Francesco Silos Labini for their contribution to this analysis.
Okay, thank you so much for the.
Thank you.
So we proceed with Eugenio Lippiello. Eugenio, are you online? Are you there? Eugenio? I don't see you. Let me see in the participants. Maybe we should go ahead with the next talk, and if Eugenio will pop up, we will move, we will give space to him. So then the next speaker is Salvatore Miccichè.
Okay, good afternoon. Can you see my screen?
Yes, yes. Thank you so much.
Okay, you're welcome.
Maybe you can go full screen.
Yes. Okay.
Okay, perfect.
And I will talk to you about global network connectivity and critical percolation thresholds in the air traffic socio-technical complex systems. So this is a work done in collaboration with Giuseppe Papalardo and Rosario Mantegna, and this is a work originated by an H2020 project, ADAP, Advanced Prediction Models for Flexible Trajectory-Based Operations. The idea is we are in the domain of the air traffic system, and just a few words to say how this system works. So you know that the airspace is partitioned in different sectors. Each sector is associated to an air traffic controller who take care about the fact that airplanes do not crash the one into the other. So the idea is that a single air traffic controller can manage in a certain time of interval of time, can manage a certain number of aircraft, and this is called capacity. So when the planning of the trajectory is done, the idea is that one tries to accommodate as many as possible aircraft in a certain airspace, given the capacity constraints of each sector. So aircraft go from origin to destination through sectors which have a certain capacity which is declared by the national authorities that control the air traffic system. So the idea is that you move from one sector to another through other sectors, and each sector has its own capacity. Somehow, this remember what happens in percolation, where you have water that has to flow from one side to another of a porous medium, and this water has to go through cavities. And we know that there is an order parameter, which is the ratio of the empty spaces over the full spaces. And according to this order parameter, depending on this order parameter, water can flow from one side to another or not. You can see better this if we model this system as a lattice. You have to go from one side of the lattice to another through nodes that can be switched on and off according to a certain probability. There is a percolation threshold, which means that if the probability of switch on and off these nodes is above a certain critical value, which is this one for a two-dimensional lattice, then you can go from one side to another, which means that there exists a connected giant component. And this concept can be translated into from lattices, from porous media to networks. And so we want to investigate the efficiency of the air traffic system using this example. We have the network of sectors. Each sector has its own capacity, and we want to study when there exists a giant component of this network, so that you can go from one sector to any other sector without problems. But if you do that, and if you study this network with usual percolation approach, you will find that there is a percolation threshold which is very small, which is in a certain sense, this is very good, because already at small values of probability, the network is connected. But sectors are not like the nodes of the lattice, because sectors are all different between each other, and sectors are different because they have different capacities. And so we want to investigate the connectivity of this sectors network, considering that sectors are different from each other. So we construct this ratio, which is the capacity of a certain sector in a certain day and in a certain time interval, divided by the maximal capacity for that sector in that time interval. This is a number between 0 and 1, and we use percolation to investigate the connectivity properties of the networks. And when you do the switch on and off of the network, rather than extracting a probability from a uniform distribution, which is what you usually do in the standard percolation approach, you extract probabilities according to the distribution of this ratio, which is empirically taken from data. For each time and for each day, we have a PDF of this ratio, and this somehow corresponds to the fact that nodes are not all the same. They have their own probability. The second ingredient in our investigation is that we consider two different approaches. We take in our network the nodes that are below threshold in one case, and the other case we take the nodes that are above threshold. In this way, we want to understand what is the process of network formation, and we have a certain threshold, and the process of network disgregation, and we have another percolation threshold. Of course, these two thresholds, T under and T over, are not independent from each other. I'm going to finish. There is a relation. There is no time to show the relation, but it can be put on solid mathematical roots. And for example, these in the network that I showed you before, we have a T under of 0.54, a T over of 0.85, 89, and the standard percolation threshold is 0.12. And essentially, this is these are all the percolation threshold in 1 year of data. And you can see that the over percolation threshold is quite high, which means in our approach that this would indicate that the multi-network remains connected even for capacity values that are close to their maximum. And we think that this is something very much related to the fact that this is a supervised system in which controllers have a big role and manage the aircraft so that they can be inside the sector, even though they are close to the maximal capacity of the sector. And there would be many other things to say, but I stop here. And eventually, if you are interested, you can contact me and I will be happy to answer to your questions. Thank you very much.
Thank you, Salvatore, for this very interesting talk, connecting percolation and this interesting problem in airspace traveling. So I think we proceed as planned, and then we will have Lippiello at the end of the event. So the first talk is Carlo Lucibello. Yes. So you can try to share your slide.
Yeah. Okay. All right. Can you see the slides?
Yes, we see them.
Okay. Hi, everyone. And in this short talk, I'm going to discuss about the recent work I've done in collaboration with Christoph Henauer at Buffoni University. I will briefly discuss a more broader theme, which is knowledge integration in machine learning pipelines. Then, as our specific contribution, I will show how you can integrate knowledge in modeling of data distribution by using energy-based models. And then we will show the results of a few applications of this approach. So what do I mean by knowledge integration? I mean, everyone knows that in recent years, I mean, we had a huge success of purely data-driven machine learning approaches, and by that I mostly mean deep neural network, in, I mean, solving many different tasks, many different applied, but also scientific domains. So, I mean, huge success, which kind of like push a little bit aside the need for developing and models and intuition of a specific problem. But that said, I mean, domain knowledge and modeling is still very important, because in some situation you have, for instance, you can have low data availability, or you may need some explanation of what's going on. You're not happy with a purely black box prediction. Or maybe, I mean, especially if you're a physicist, you're really interested in like developing models, because by modeling you kind of presume the main features of some problem, then you test and increase your understanding of the world. So, I mean, there's kind of a like developing field where you try to combine like black box modeling and also classical modeling. So you have a machine learning pipeline, you have a specific task, you have data, you want to inject your specific knowledge of which could be in which could come in different form. For instance, this is an example where you have some data which is generated by some differential equations. We have samples from this differential equation, but then maybe you are not in a zero knowledge situation. You know that some terms in the force driving the system, so you explicitly model these terms, and then you stick for each unknown. You stick just in the force some neural network, which you have to then feed to the training data, and then after you feed, you see that the neural network is able to predicts also for very large types, much beyond the time horizon of the training data, is able to predict the behavior of the system. So here you have some partial knowledge, but you also have some black box approach. And we kind of do the same in a different setting where you have instead probabilistic knowledge of some distribution of data. So you have data, your task is to infer some, to fit some model among some distribution family to this data set. You have some prominent approach in machine learning, which have some pros and cons, but every one of them has the flow that is not composable. It's purely black box, and you cannot kind of use the neural network as a like perturbation to some prior knowledge, prior assumption that you have on the specific probability family. So what we did is to use kind of a different type of modeling. Let's use model, which is an energy-based model, where you just model the energy function, so the log probability instead of the full probability distribution. And in our setting, the knowledge is injected as some explicitly known parts of the energy. So we know that there is some pairwise part in our energy, so we explicitly model it, and then we add to that a black box, a neural network which just can account for maybe higher order interaction. So while the real data can have like pairwise coupling and then some like order 3, order 4, and so on interactions, in our modeling, we explicitly model the pairwise interaction, but then we capture the rest of the system with a neural network. Then we fit this hybrid model. And yeah, I mean, we get some interesting results. In fact, for instance, if we try to reconstruct in a synthetic setting the pairwise coupling in the original data generative distribution, we see that when you do use just a pairwise model or just a multi-layer perceptron, well, you don't reconstruct very well the coupling. While if you use the hybrid approach, well, in that case, I mean, you do much better. Another setting we tested is in the case of proteins, because proteins are very well modeled by a POTS model, so by a pairwise model. But you also know that in protein families there are some higher order interactions. So while like pairwise interaction, they do describe pretty well contacts between amino acids when the proteins are folded, so the strength of a coupling is a good contact predictor. The data, I mean, contains also some higher order interaction terms, which you don't know in advance. So we used our hybrid approach and try to infer the contacts. And what we see is that when trying to with the predictive positive value is much higher in our hybrid model. So we infer much more contacts than by using a simpler pairwise only model. Okay, and this is, I think, pretty much all I wanted to say. So just use energy-based models because they are good candidates for knowledge integration, since they essentially, you can compose some physics-inspired part. So for instance, a pairwise part and some black box term for accounting for the higher order interaction for the generic unknowns of the data. Okay, thank you for listening.
Okay, thank you so much. Very nice combination of pairwise and higher order interaction. The next speaker is Deco Alberici.
Yes.
Are you here? Yes.
Yes.
You can try to share your slide.
Okay, can you see the slides?
Yes, yes.
Okay. Thank you very much. Thank you for this nice opportunity. I'm going to talk about random deep Boltzmann machines, presenting some analytic results in the replica symmetric region that were obtained together with Contucci, Mingione, and Barra. What is a deep Boltzmann machine? So take n binary variables, sigma 1, sigma n, which are called spins, neurons, or units, and arrange them along k consecutive layers, L1, Lk. Each pair of variables, sigma I, sigma j, belonging to 2 consecutive layers, interact according to a certain weight, Jij. The system can be described by an Hamiltonian Hn, which is the sum over all the pairs Ij belonging to 2 consecutive layers of minus Jij, sigma I, sigma j. As usual, in statistical mechanics, we can then introduce a Gibbs measure of the set of spin configurations and a partition function denoted by Z. An important quantity to describe the system is the overlap of 2 different configurations, sigma and tau, restricted to each layer Lr. This quantity, denoted by Q, is defined as the scalar product of sigma and tau restricted to the layer Lr and properly normalized. An important application of deep Boltzmann machine is, for example, image recognition or reconstruction. A training set of suitable images is considered as typical realization of the first layer units. And then all the interactions Jij are computed along the network, trying to minimize, for example, the divergence between the empirical measure of the training set and the marginal Gibbs measure on the visible units. This is an example by Salakutinov and Hinton, where on the right you can see some training samples, and in the other 2 pictures you can see some images constructed by suitably trained Boltzmann machines. From a statistical physics perspective, we would like to understand and study the direct problem before dealing with parameters reconstruction. To do that, we make 2 main assumptions to simplify the framework. The first one is that the interactions Jij are independent centered Gaussian random variables with variance allowed to depend on the layer. And we arrange those variances along this 3-diagonal matrix denoted by delta. The second assumption is that of thermodynamic limit. That is, we let n goes to infinity, but we assume that the relative sizes of each layer is kept fixed, and we denote it by lambda r. First property of this model is that the Hamiltonian can be seen as a centered Gaussian process, whose covariance is a quadratic form in the vector of the overlaps. The quenched pressure concentrates around its average, denoted by Pn, and defined as 1/n, the expectation of the log of the partition function. And if we take the log inside the logarithm, we get the annealed pressure, which is a much easier quantity to compute. In case the vector of the overlap vanishes in a suitable sense, then the quenched pressure converges to the annealed one. For application, it's important to remark that in this case, no image recognition or reconstruction is possible. So we call annealed region the set of parameters delta and lambda such that the quenched pressure coincides with the annealed one. And we managed to characterize this annealed region as with the condition that the matrix delta times lambda has spectral radius smaller or equal to 1. In application, one may ask how n units can be arranged on different layers in order to minimize the possibility to fall into the annealed region. In this framework, we can answer with this proposition that describes 2 possible optimal architectures. The first one is given by only 2 consecutive extensive layers. Each one of them has half of the total number of units. The second architecture is given by 3 consecutive extensive layers, where half of the total number of units is arranged on the middle layer. To conclude, those results were obtained thanks to a lower bound for the quenched pressure of the deep Boltzmann machine in terms of a variational principle involving k-independent Sherrington-Kirkpatrick models coupled in temperature. Thank you very much.
Thank you so much. Thank you so much for the interesting talk. We go back to Eugenio. Are you here now?
Yes, I hope to be here. Okay, sorry, Ginestra. Sorry to all of you for this inconvenience. I don't know what has happened, but a problem with Zoom, and I had to reset everything to go back. So sorry for the inconvenience.
Fantastic. Can you share the slide now? Or?
Yes, I hope so. You can see it, sorry.
Yes, if you go full screen, maybe it's good.
Okay.
Okay, perfect.
Okay. So again, sorry to all for this inconvenience, and I want to thank the organizer for the opportunity of present these results that are substantially new criterion to identify cluster within an epidemic structure. And just to have a look how an epidemic evolves, so one starts from one element with usually termed the ancestor or patient zero, and then this ancestor infects new people, so one has a new infected that are localized in space around him, and these are the offsprings, the descendants, and as time goes on, the number of elements increases, and at a given time, a new element, a second immigrant, comes into play, and then a new cluster, the red one, grows in this position, and as time goes on, the black and red cluster continues to grow, but a third one appears, and so a fourth one. At the end of the history, we have many clusters with a very complex spatiotemporal organization. And so our task is to discriminate between immigrants from offsprings. So we want to identify the immigrants within this kind of complex structure. And this allows us to answer one fundamental question in cluster analysis, that is how many immigrants are present, that it's fully equivalent to ask how many clusters are present. And we address this question by supposing that we know the mathematical model, which controls this epidemic evolution. In particular, I consider the very general model for epidemic introduced by Kermack, McKendrick, and Walker in 1927, which is nothing else than the famous Galton-Watson branching process, where we have two terms. This term here substantially controls the birth of new immigrants, whereas this terms is the element of the similarity matrix that substantially is inversely related to the distance, to the spatiotemporal distance between the two elements. And okay, supposing that these elements are known, there are many methods developed in the literature to identify the optimal number of clusters. Here are just a list of them. And the basic problems with this kind of system is that they are very time consuming, and also they need a huge memory storage. And that's why this method can become very complicated when one has to deal with a big data set. And now we present a new strategy to overcome this difficulty that is substantially based on the evaluation of the likelihood. Here is the likelihood, the usual likelihood, and now we introduce this approximated likelihood that substantially corresponds to replace to the similarity matrix, a new matrix that I call QAJ, which presents a lot of zeros. In particular, I put 0 to all the elements which are below a given threshold. PTH is a fundamental quantity because, for instance, this quantity allows us to define an immigrant. An immigrant is substantially an element which has all zeros in the row with respect to all previous elements. And okay, now we construct from these two quantities the difference of the log likelihood of the two quantities, and this from analytical arguments is possible to show that this quantity has a very peculiar behavior as a function of this P threshold. In particular, we can identify two elbows. The first one substantially corresponds to a configuration when the number of clusters that one can define in this approximated matrix exactly corresponds to the number of clusters in the true partitioning of the system. Whereas this second elbow here corresponds to a situation when substantially we can say that at this value, P2, we have that two elements can belong to the same cluster only if their element in the similarity matrix is smaller than P2. And we have verified that this situation is found for different epidemic models, in particular also for this epidemic type aftershock sequence model, which is commonly adopted to describe the very complex spatiotemporal pattern of seismic occurrence. And we have verified that for a wide range of parameters of the model, we always find this peculiar shape, and which corresponds to the optimal number of clusters within the system. And so I go to the conclusions, illustrating the advantages of this approach. Substantially, this is a very efficient method, which is often a better result with respect to standard method to identify the optimal number of clusters. And but the main advantages is that it's very fast to implement numerically, and in particular, it does not need any use of the memory. And so substantially, this, as anticipated before, is a big advantage when one has to manage with the big data sets. And okay, you can find detail in this preprint, and thank all of you for the attention, and thank again the organizer for the opportunity of this presentation. Okay.
Thank you so much for the interesting talk. I want to thank all the speakers of this session. We had a very diverse and interesting profile of landscape of interesting topics. So a big clap to all of them. And as expected, we are a little bit out of time, despite I've been quite nasty. So I don't know, the break, maybe Raffaella, you want to tell us about the break?
We can resume at the usual time that we.
Okay, so this was, I think,
5:10.
5:10.
Past 5, yes.
In 4 minutes.
Okay.
Okay.
Okay. Thank you, Jeanette.
Time of a coffee. Thank you again to everybody, and bye. Bye.
Bye.
Good afternoon. We decided to wait a few more minutes since we were late with the last session. Okay. So we will wait until 5:15 and then we'll start. Okay.
Can I try to share my slides?
I think we can start now because it's almost 5:15. Okay. So this will be the last session for today. I am Irene Giardina. I will be your chairwoman. Our first speaker in this session is Giacomo Livan from University College London, and he will discuss leveraging academic networks to understand scientific impact.
Hi everyone. Good afternoon. Can you see my slides?
Yes, we can.
Okay. Thank you. So yeah, first of all, I would like to thank the organizers for giving me the opportunity to present my work here today. So I am affiliated to a computer science department and an economics institution. So obviously my research is interdisciplinary, and today I would like to give a bit of a perspective on some of the things I do. In particular, in recent years, I have been interested in modeling and quantifying reputation in social systems. And I found out that academia and science are obviously very reputation-driven systems, and therefore it's interesting to study them from this perspective. So what I would like to talk about today is basically leveraging data that detail academic networks in order to model, quantify, and understand scientific impact. So what I should start from first is definitions, or I should say lack thereof, because of course, scientific impact is a very qualitative concept, and depending on who you ask, you will get very different answers. Some people may relate it to the process of discovering science, whereas others may have a more pragmatic point of view related to publications, for example. In this talk, I will take the very narrow but precise perspective of that is often adopted in several countries, which is, and that I do not necessarily endorse, by the way, which is that of quantifying scientific impact with the citations accumulated by publications and by scientists, and the indicators that we can compute starting from them that we are all familiar with. So the H-index for researchers, the impact factor for journals, and so on and so forth. So before I talk about some results, I would like to set a bit of the stage for what I'm going to do. So first of all, I guess we should start from this question. So as physicists, why should we care? Well, I would say, first of all, out of curiosity, because now we have excellent data sets that allow us to study science, so study the very system that we are a part of. And second, because citations and all the indicators that I'm going to talk about nowadays influence all aspects of academic decision-making, either formally or informally, depending on which country you're based in. But essentially, when I say this, what I mean is that these indicators, to some extent, determine who is hired, who is promoted, and in some countries, there are even they even influence salaries because there are bonuses given to researchers based on their metrics of impact. So there is a very long history of studying science and scientific publications from a quantitative perspective. It dates back at least to the 50s. And of course, over several decades, it has evolved into very well-established fields of research, normally known as scientometrics and bibliometrics. And typically, these fields of research are mostly grounded in the social sciences and adopt methodologies from the social sciences. However, in recent years, people from physics and from statistical physics in particular became interested in these disciplines. Mostly, I should say, because of the increased availability of very interesting data sets, as I've mentioned. So, for instance, a few years ago, this review article was published in Science, aptly titled Science of Science. And as you can see, from the list of authors, you can easily recognize some very familiar names from the statistical physics community. And this article covers all the aspects of the science of science that have been covered by these people. If I should say in one word why I think people with a statistical physical background are well equipped to study problems in science of science, I would say networks. Because if you think about it, academia and science are essentially networks, meaning the collaborations, the co-authorships, the conferences that we used to go to or do online, they're all networks of some kind. And again, this is a very old observation. So even in the 70s, you had Merton, one of the first people to become interested in these things, that was talking about so-called sociology of science. So the essentially the set of relationships, of social relationships that make science happen, that make it possible. And of course, now nowadays, several decades later, the main difference, which I keep stressing, is the increased availability of data sets, thanks to which we can quantify much more precisely all these aspects. And with a statistical physics background, allow you essentially to study these things from the perspective of network ensembles deploying all the well-known machinery to in that respect. So now finally, let's come to the research questions I would like to address in this field. As I've said, I want to study the relationship between impact, or I should say metrics of impact, the one I have introduced, and quantities that we can compute from academic networks. In the first part of the talk, I will look at academic networks as a coordination mechanism. And what I mean by that is I want to see if we can detect statistical evidence of, let's say, collective response of the academic community in the last few years due to the increasing pressure that academics face nowadays to essentially attract more and more citations and boost their scientific impact. In the second half, I will instead look at academic networks as, I will call it an inheritance mechanism. So I will look at the early stages of an academic career. So I will look at early career researchers and their early career social network and see if their long-term career success and impact can somehow be traced back to that start, to their early career network. So without further ado, let's address the first question. So let's look at this problem of coordination. So the way I would like to think about this is the following. We have seen in recent years a variety of examples of what happens when you measure performance in social systems. One example is, for instance, factories that implement productivity targets for their workers. We know that there are unintended consequences to that, meaning that workers ultimately burn out in order to meet their targets and become exhausted and therefore less productive. So eventually the whole thing backfires. Another quite worrying example is in the US and UK, where surgeons are ranked based on the mortality ratings of their patients, which ultimately disincentivize them to perform the most complex surgeries. So they just don't do them. And of course, that is detrimental to patients. Now, the way I like to think about all of these unintended consequences is under the umbrella of the so-called Goodhart law. Stated first by an economist, Goodhart, which states that when a measure becomes a target, it ceases to be a good measure. What that means in practice is that when you are ranked and are aware of being ranked according to a metric that you can act upon, then that metric effectively stops measuring your performance, but rather measures only your ability of optimizing the metric itself. A couple of years ago, I have published a simple model, a simple computational model of a synthetic society whose individuals try to basically play this game. So they are aware of being ranked, and what the model shows is essentially Goodhart law, the Goodhart law in action. So the more the agents place importance in the ranking, well, this backfires, and ultimately the whole society becomes less meritocratic, we could say. So the correlation between the intrinsic fitness and skills of the agents and their ultimate placement in the ranking decreases with this parameter. So finally, let's look at this from the perspective of academia. An example I think is quite instructive is actually Italy, which about 10 years ago introduced reforms that introduced a very indicator-oriented system, so that associate and full professorships only become available to candidates that meet certain bibliometric thresholds with their indicators. And unsurprisingly, let's say the reaction has been observed, and it has been a spike in the rate of self-citations. That's an obvious response, and that's another example of Goodhart law, this time in academia. So I want to build on this and see if we can detect something more systematic and at more large scales. In particular, I want to see if we can detect evidence of coordination that goes beyond the individual, so beyond self-citations, and cast this initially as a problem of reciprocity in a network. So I am going to model citation networks of authors like this. So for instance, in this picture, suppose we have two scientists, I and J, that over a certain period of time have cited each other. I has cited J 5 times and J has cited I 8 times, let's say. And then let's say you want to measure how much and how often these two scientists have reciprocated citations to their respective work. Well, a possible score is the one shown at the bottom of the slide, where you just take the lowest of the two links on the network and normalize it by the total exchanged weight. However, this is not a great definition of reciprocity precisely because it doesn't take into account network structure. In particular, first of all, it doesn't take into account the distribution of weights that we have on the edges. And it doesn't take into account structure in the sense that, of course, we expect a lot of reciprocity happening between scientists that work in similar fields, so in the same scientific communities. And this particular indicator would not account for that. So thankfully, we have papers that tell us what to do. So here I am relying on work published by Garlaschelli, Squartini, and their collaborators that essentially allows us to introduce a score of excess reciprocity, so an excess with respect to a benchmark. And this is simply encoded like this. So we take the naive definition of the previous slide, so just this normalized ratio, and subtract to it the same quantity but computed in an ensemble of suitable null network models. So what I mean by that is we will take the empirical citation network of the authors, and we will partially randomize it. When I say partially, I mean that we want to keep some of the properties of the empirical network fixed, and those properties are meant to encode the natural citation practices which I mentioned. So first and foremost, the fact that people within the same communities should cite each other at fairly high rates just because they acknowledge each other's work. I cannot stress enough that here the null model is the key ingredient. So the assumptions that we make, and again, the citation practices that we think are okay, will be encoded in that, and everything else we will try to randomize. The data we start from are interestingly physics data. So it's the whole corpus of APS publications in the 60 years from 1950 to 2010, which amounts to more than 400,000 papers containing more than 4 million citations between them. And this is how the null model works. So first of all, I should say we start from papers as the main units that give and receive citations, and then we will project that onto a network of authors, of scientists. So the way we do it is we select pairs of papers at random, as shown in panel A, pairs of paper at random where citations happen. So here P1 cites P2 and P3 cites P4, for instance. And then what we do is we swap those links, as shown in panel D, if the new links we are placing in the network, so P1, P4, P3, P2, match two constraints that we place on the network. One is a constraint on time ordering. So we only accept the new links if and only if newer papers cite older papers, because of course the opposite cannot happen. And second, we implement a distance constraint in order to enforce what I mentioned. So the fact that people that are close in terms of research interests are supposed to cite each other quite a lot. So we implemented this constraint in a variety of ways, and the results are qualitatively identical. So what I'm going to show here is a constraint based on distance. It means that we accept a new link, for instance, as shown in the link between P1 and P4 in panel D, if it is placed between a pair of papers that share one author. So there's a little guy in red, that's the same author. Or we also accept a distance 1 constraint, meaning we accept the new link if the two papers it connects have authors that have cited each other in the past in the citation network. The nice thing about this null model is that while preserving these constraints, it also preserves for free a number of properties. First and foremost, the number of citations received by each paper and author. And that essentially means that we preserve the impact of everyone in the network. So essentially, what we are doing is we are creating these null network model configurations. Of course, we do a bunch of them to create an ensemble in which everyone has the same scientific impact, but it has been achieved through potentially different citation patterns. And what we want to see is the difference between those patterns and those observed in the empirical network. The first thing we look at, well, is we ask whether we do detect excess reciprocity in the whole network. These are annual snapshots, so we repeat this exercise year after year for the 60 years in our analysis, and the answer, as you can see, is yes. So every time the excess reciprocity score is above 0, that means it is in excess with respect to the null model benchmark. But the interesting thing that you can see is it starts fairly low and almost compatible with the null model in the 50s, and it steadily increases for more than 40 years before stabilizing around a roughly constant value. So somehow telling you that there has been an increased attention towards citations, and this may be one of the responses to that. Then we may ask, what are the main drivers of this reciprocity? One of the main drivers is reciprocity between co-authors, which we checked. So this is what this plot shows. On the x-axis, we have essentially a proxy for the, let's say, overlapping research interests between pairs of researchers. So we take all the pairs in our data set and compute the score, which is essentially looking at all their history of publications and all the papers that they have cited, and we compute the similarity between the two lists, which gives you obviously a proxy of how close or far apart they are in terms of interests. That is on the x-axis of the plot. The y-axis shows the reciprocity between these two these pairs of authors. As you see, the relationship is increasing, as you would expect. So the more people are close to each other, the more they cite each other, as I said. However, interestingly, there is a statistically significant gap when you look at co-authors and non-co-authors, with the former citing each other at a significantly higher rate. Then we come to what was, let's say, the motivating question, which is what is the relationship between this excess reciprocity and impact? Here we look at that at the level of individuals. So here the bins you see with error bars are a group of individuals, of researchers. And on the x-axis, we have the citations they have accrued over a certain decade. And on the y-axis, the reciprocity, excess reciprocity score measured now at the level of individuals. So how much their reciprocity pattern deviates from what the null model predicts. The relationship is plotted over 3 different decades, 50s, 70s, and 2000s. And as you see, things have changed quite dramatically over the years. In the 50s, this is a statistically flat relationship, meaning there is no difference whatsoever. Interestingly enough, it is quite close overall to the null model. It is just slightly above 0. If you flash forward to the 2000s, this has changed. This is now a markedly negative relationship, which tells you that those who are cited the most are actually those that reciprocate the least, and vice versa. So in a sense, this leaves us with, I would say, an optimistic message. So even if you wanted to, let's say, reciprocate your way to a lot of citations and to a very high scientific impact, well, this plot tells you chances are this strategy wouldn't work. It still seems, luckily, that you need good papers in order to get recognized quite a lot. We now want to look at the same problem, but from the perspective of journals. So now the metric of interest is the journal impact factor. So essentially an average over the citations received by papers published over 2 years. And I think this is interesting because there's been quite a lot of anecdotal evidence of so-called citation cartels. So a group of journals coordinating in order to, force more citations being received by their published papers. And ultimately, this has even led Thomson Reuters in recent years to ban a number of journals or groups of journals for clearly manipulatory practices. What we want to do here is to try to see if we can detect more, because the list of journals banned by Thomson Reuters is quite short. So we want to see if we can detect more anomalous behaviors. The challenge, like in the previous analysis, is now detecting an excess, because of course here we are trying to detect communities, tightly knit communities, in a world where communities are the norm, because of course published science is organized around groups of journals where we expect citations happening at high rates just because they are journals in the same field. So again, we will need a null model. The data we are using here are 48,000 journals that have been active in the 20 years from 2000 to 2019. And what we're doing again is annual snapshots, annual journal citation networks, where the weights on each link are the number of citations given by all the papers published in a journal to all the papers published in another journal over the previous 2 years, because again, that's the period used to compute impact factors. Overall, we tried to do this by designing a simple algorithm, which we called cider, not necessarily because it's also the name of a delicious beverage, but because it stands for citation, donors, and recipients. Because we started from the perspective that potentially anomalous groups may be formed by both donor and recipient journals. So journals that provide or receive citations within the group at excessively high rates. The algorithm works like this. You take the full network and then deplete it by removing all the nodes and edges that are compatible with a null model. And the null model is the degree corrected stochastic block model. I don't have time to go into the details, but that's essentially a community detection model. So it naturally breaks down the network into communities, and those communities are basically disciplines. This is well known. It captures this aspect quite well. So essentially, you look for anomalies with respect to that, and you remove everything that is not anomalous with respect to this community structure. Then you compute these donor and recipient scores for all the journals. These are the scores shown in the two equations, and these are just the fraction of outgoing and incoming citations for each journal I within the group. You do this the first time, treating the full network after this depletion as the group G, and then you keep dropping all nodes whose donor and recipient scores fall below a threshold. You keep doing that, and that ultimately will leave you with no further nodes that can be removed, and will break down the network into disconnected communities. These are your candidates for anomalous groups. So first of all, let's say a quick look at the big picture. So what we found over the 20 years of our analysis is about 880 groups that we detected. You see in panel A the number of groups we detected each year, and in panel B the box plot distributions for their size. And as you can see, they are fairly small, as you would expect, just a few units per group, but with a few outliers of order 10 or a few tenths of papers. So the first thing we want to do is to compare the groups detected by CIDR with the ground truth provided by the list of banned journals, or banned groups, I should say, by Thomson Reuters over the years. This is shown in the plot here, where the blue empty circles denote the groups banned by Thomson Reuters, and the colored dots denote the groups detected by CIDR. Shading denotes the amount of overlap between the two. Anything with an overlap above 50% we call a detected group. Over the years, we detect 12 out of the 22 cartels banned by Thomson Reuters, which may look not like a non-fantastic success rate. However, once you inspect the other 10 groups that go undetected, you understand why. And the reason is that precisely because they were banned, that led to a lot of paper retractions, and ultimately those papers disappear from the very data that we were trying to use in order to detect these groups a posteriori. However, chances are that if applying CIDR in real time, we would have been able to detect these groups. And I say that because, as you can see in the plot, the groups that we do detect, we typically detect consistently for 2 or 3 years in a row, and typically a couple of years in advance with respect to Thomson Reuters. So overall, I think this provides a better context, and therefore we could say it gives us confidence that this algorithm, CIDR, works quite well. Then, therefore, we want to see why do we detect these groups? And here we try to provide a simple classification, kind of little ecology of these anomalous groups. You see the breakdown based on type, both for those detected by CIDR only and those detected by Thomson Reuters. We split them up into 6 groups. So groups A and B are essentially anomalous groups that are such just because of one paper. So you essentially can identify one donor paper in the case of group A, or recipient paper in the case of group B, that is single-handedly responsible for the anomalous behavior, because it either provides or receives 20% or more of the within group citations. The group we labeled C and D are the same, but in the case of single authors. So there is one author alone that either provides or gives or receives 20% or more of the citations within the group. Group E is also interesting. It's cases in which we find pairs of journal in the anomalous group that share one or more editorial board members. And then group F is just what we couldn't classify according to any of these criteria. I want to show some examples. So this is an example from group A, which I remind you is cases in which you have one donor paper that is basically single-handedly responsible for the anomalous behavior of the entire group. This is a group of 8 journals in the humanities where you have one donor journal that published a donor paper that alone basically contributes to more than 57% of the impact factor of the recipient journals. And if you look closely and take a look at that paper, you see that it's 42 pages long, and 40 of those 42 pages are just the list of references. Another example is from Group C, which is essentially the same mechanism, but at the level of authors. So there is one person who is essentially providing citations, so many citations that essentially creates the whole anomalous group. This is an example of 5 journals in engineering where we detected one author who basically wrote a third of the papers providing the within group citations. And in the process, self-cited their own work more than 300 times. So effectively, these the donor citations are the self-citations of this individual. And interestingly enough, this individual happens to sit on the board of a journal that is both a donor and recipient member of the group. So let me wrap this first part up by trying to draw a few conclusions and lessons that we learned in these 2 studies. I would say, first of all, it's very important to make a disclaimer, which is that we didn't prove that either scientists or journals cheat. What we detect here is only evidence of statistical evidence of trends that are visible over the years. So this is the pro of the analysis, because you can do basically big data analysis on all these publications. So you do detect trends with reasonable statistical confidence. However, the cons is that, of course, this doesn't allow you to draw definitive conclusions of detection of explicitly malicious practices. That would require a specific investigation on a case-by-case basis. Well, a lesson that we learned, however, the lessons that we learned, however, from these studies, I would say from the first one is there is a lot of excess reciprocity. It has been increasing, but it doesn't pay. So as we saw, reciprocity alone wouldn't make you a highly recognized scientist. And in the second case, in the second study, we came up with a simple yet effective algorithm that provides a useful tool which could complement then human judgment when basically by providing candidates for cartel behavior in journal networks. So overall, I think the overarching lesson that we learned is that we are detecting, so the statistical trends we are detecting, I think, are just Goodhart's law in action in the sciences. And again, I remind you, it's the fact that when there is a clear target to measure performance, then it ceases to be a good measure of performance. And I think this is precisely what we are detecting with these analyses. So the conclusion we draw from this is that when we look at citations and indicators, we should always try to see where they come from, how they came about, and never take them just at face value, I would say. And I will try to to basically reach the same conclusion now in the second part of the talk, where I want to look at academic networks as an inheritance mechanism, so to speak. So the way we're going to do this is by looking at the early career of junior researchers in the sciences. And we are going to do it with a statistical technique known as matched pairs analysis, which interestingly is fairly similar to what is done to form groups for clinical trials. So suppose you want to test the effectiveness of a new drug. What you do, and we have seen it with all the vaccine trials recently in the pandemic, what you do is you form a treatment group, so people that receive the drug, and a control group that only receive a placebo. However, especially if you're working with small samples, you do not want to form these groups at random because, for example, you may be unlucky and you may just by bad luck assign all the smokers, let's say, to the control group, so to the treatment group, and that may make the effectiveness of your drug look lower than it actually is, just due to bad luck. So what you do is you typically try to identify pairs of individuals that are almost identical with respect to all the variables that matter in your analysis, and then you allocate one to the treatment and one to the control group. Here we want to do exactly the same thing by taking early career researchers in the sciences with almost identical early career profiles across 3 dimensions that tell you how an early career is going. So early career citations, productivity, so the number of papers published, and a score that quantifies the institutional prestige of the researchers' affiliations. And then we do exactly as in the trial example, the following exercise. So we form these pairs in such a way that one member of the pair has published early on in their career a paper, just one paper with a so-called top scientist, I will clarify in a second, and the other member of the pair doesn't have such a paper. And what we want to see is the long-term impact that such an event has on a career. Definitions. When I say junior researcher or early career researcher in this analysis, I am referring to someone in the first 3 years of their career, which roughly coincides with a PhD in most places. Top scientist here is just a shortcut to say someone who is in the top 5% of cited scientists in their field. And given what I have said so far, it should be clear by now that I do not think personally that in order to be a top scientist, you need to be there. All I'm saying is this is just a quick name to identify someone who is highly cited. And when I say institutional prestige, I do not want to go into too much detail. This is a score derived from an index published by the Nature Group that quantifies the perceived prestige of an institution thanks to a number of factors. If you look at the rankings that you get out of that, it makes sense. It gives you the usual suspects that you would expect at the top, such as the Ivy League universities in the US. By the way, all of the results are fairly robust to modifications in these definitions. So the data we look at here are data of publications in 4 disciplines in the sciences. I stress in the sciences because let's say in the social sciences, things would look very differently. And what we are looking at here is, of course, only people with long-lived careers. We are interested in seeing what happens after this early career event many years down the road. So we restrict to the group of 22,000 or so scientists that we found in these 4 disciplines that have had such long careers. So I will spare you the table that actually presents the results from the matched pairs analysis, because that's just a long list of numbers. I will actually present a simpler version. This is just a histogram that summarizes the same results quite well. And basically, we do not lose much by just looking at this, but it's a lot more user-friendly. So this histogram shows the all of our 22,000 or so early career scientists broken down into 8 mutually exclusive groups. These are the groups you see on the x-axis. You see these little letters, IPC. These are the 3 dimensions that we used for the matching. So the institutional prestige, I, the productivity, P, and citations, C. Then if we start, for example, from the rightmost group labeled as IPC, those are all of our early career scientists that are in the top 10% in all 3 dimensions with respect to their cohort in their discipline. Then if you move one step to the left, for example, the group PC are those that are in that top decile only for productivity and citations, and so on and so forth. And you get all the way back to the group labeled as none, which is obviously by far the most numerous group. Those are the early career researchers, which are not in the top 10% of any of these 3 dimensions. Then you see that each of these groups is split into 2 subgroups, the 2 beans painted in brown and purple. They are labeled as yes, no. Yes means that that's the subgroup of people that have that paper in the first 3 years with a top scientist, and the group labeled as no, shown in purple, are those that don't have. And on the y-axis, we have the probability for those people to be top scientists themselves 20 years down the line. So we flash forward 20 years. The probabilities look very high here, and that's because there is survivorship bias here, meaning the fact that these are all people with long-lived career, and that alone gives you already a fairly high probability of being highly cited in your 20th career year. So if we start from the group on the right, so the people who start their career, let's say, in the best situation, you see that the 2 subgroups are identical in terms of probability. So to them, it doesn't really make a difference whether they do have or not have this one paper with a top cited scientist. And the probability in absolute terms for them is very high. Then this probability decreases as you go from right to left. And interestingly, also the gap between the two subgroups, the yes and no subgroups, increases. And let's go all the way to the left. So let's look at the group labeled as none. You see that in absolute terms, the probability for this group of becoming highly cited is much lower in absolute terms, but the relative difference caused by this in single paper published in the first 3 years is enormous, because it essentially doubles this probability from about 12 or so % to 25%. So it really makes a huge difference, and it represents, from this perspective, a potentially career-altering event. So what conclusions can we draw here as I wrap up? I think this second half, this result shows us a conflict between a chicken and egg problem, basically. We have two possible interpretations of these results. So interpretation one would be a more causal interpretation that tells you that it is working with a top scientist that causes greater impact down the line. Whereas the alternative interpretation is that what we're seeing here is already the result of early career brilliance. So for instance, you are an excellent student in high school, at university, then you get recruited by the best PhD programs, the best supervisors. So you're already reaping the results of your early career brilliance. However, in principle, the technique we have used is a causal inference technique, and also the sheer extent of the effect suggests that while both interpretation are at play, interpretation number one is probably the one that is the most plausible and the most frequent. The big disclaimer here is that, of course, this doesn't mean that impact achieved through collaboration with top scientists is not deserved. I stress that what I think we're seeing here is a sliding doors effect that shows you that if you get this opportunity, so if you are in the right place at the right time to collaborate with someone who is highly visible and highly cited, that can provide you with a career-long competitive advantage with respect to your peers, which is detectable many years down the line. So again, I think the take-home message after all of this is very simple, in my opinion, and that is that when we look at correlations, citations and scores that we can derive from them, we should always place them into context and ask what factors may have contributed to them, especially because some factors, such as in this study, may not entirely be within the control of a researcher. So this is it from me. I would just like to stress to show the list of papers that have somehow to do with what I've talked about today. The first three in this list are those that I presented in this seminar. Then, of course, I would like to thank all the collaborators on these Science of Science projects, those that are already published, those that are ongoing, and you haven't seen them yet, but I would like to thank all of them, in particular in the top left, Wei Hua, who was my postdoc at UCL and was the major driving force behind most of the research, and also Fabio Caccioli and Tommaso Aste, my other Italian colleagues at UCL in our group, who have shared this research with me. So that's it from me. I thank you very much for your attention, and I would like also to thank the UK Research Council for funding my research and making it possible. Thank you very much.
Thank you, Giacomo. And we have time for a couple of quick questions. So if anyone has a question, please come forward.
May I ask a question?
Sure.
Sure.
This is a sort of a simple question. In the first part of your talk, well, maybe first to comment. I don't know if it's appropriate to talk about science of science, but this is another, say, more epistemological issue. But instead of a technical question, just the following. The first part of your talk, did you also explore, say, how the results depend on the geographical region you consider? Yes. Say, you may expect that in some less developed countries you have more effects as those you described, and hopefully in more developed countries you have less. Thanks.
Yes, we did in the first study. I presented. It's one of the many controls that you can find in the supplementary material of that paper. We did check based on affiliation, and we found all of the results to be very robust. So if you look at reciprocity at the national level, it's still there. We didn't check for journals, though. In the second study, we did not check that. Thanks.
Thank you. Any other question? Okay, then thank you, Giacomo, very much for your talk, and we can
thank you.
We can pass to the next speaker, who is Maria Chiara Angelini from the Department of Physics of Sapienza University. The topic is slightly different, and Maria Chiara will talk about loop expansion around the Bethe solution for disordered models. So Maria Chiara, if you want to share your presentation. We can't hear Maria Chiara. Okay. Okay, that's perfect.
Okay. So can you hear me? Yes.
Yes, yes. And I will now disappear when you see my face again. This means that your time is ending. Okay.
Okay. Okay, so thank you, Irene. Thank you to the organizer for this nice opportunity. And today I will talk about a series of works that I've done in collaboration with all these nice people. And I will talk about a new loop expansion that we have introduced around the Bethe solution for disordered models. So usually the standard field theoretical approach, the renormalization group approach to second order phase transitions works as follows. So you take your model, for example, an Ising model, then you can identify your order parameter that in the case of Ising model is just the magnetization, so it's a scalar field. Then you should identify the symmetries of the model. In the case of the Ising model is the spin flip symmetry. And then with the field and its derivatives, you should construct the most general Lagrangian that is compatible with the symmetry group. So in the case of the Ising model, this is the Lagrangian then you construct. You have this spin flip symmetry, so you can just put on your Lagrangian even powers of the field. So this Lagrangian has a bare part, a Gaussian free part, and then it has an interaction term. So at high enough dimension, so up above the upper critical dimension, the physics of the system is just controlled by the bare Lagrangian, and then the interaction part becomes important at low enough dimensions. So you can perform a small g expansion. G is a parameter. You can perform a small g expansion. You can use the usual field theory techniques of Feynman diagrams, and you can see when this interaction part becomes important. And in this way, you identify the upper critical dimension. Below the upper critical dimension, the mean field fully connected solution should be modified. And then you can compute the critical properties, for example, the critical exponents in an expansion around the upper and around g equals 0. And then you can also identify the lower critical dimension below which you don't have a transition anymore. So maybe many of you do not know that this Ginzburg-Landau expansion can also be recovered in a really different way with this M-layer construction around the fully connected model. So this is the work of Brezen and collaborators, and it's really nice. So you can take your model on a d-dimensional lattice, then you can replicate your lattice. For example, here you can take a b-dimensional lattice, then you replicate m times, here m is equal to 3. And then if a link ij is present on the original model, you should add to your replicated model all the links between all the spin I and all the spin j from any of the m layers. So in this case, when m goes to infinity, the connectivity of your replicated model goes to infinity. So you start from an Hamiltonian and you can write your replicated Hamiltonian adding all these links. And then you can write your partition function that will depend on this parameter m, that is the number of layers that you put. And in the large M limit, you can solve the model just with the saddle point. So the saddle point solution in the large M limit recovers the fully connected solution, the mean field fully connected solution. And then you can study the 1/m corrections around this mean field fully connected solution, and you recover exactly the Ginzburg-Landau expansion that we saw in the previous slide. So the usual field theoretical approach can be recovered with this M-layer construction around the fully connected model. Recently in this paper, we introduced a slightly modified M-layer construction around the Bethe lattice that works as follows. So you take your model, then you replicate your lattice, and then if a link ij was present in your original model, then you do a random permutation of the links between spin I and j among the M layers. So this is an example. In this way, the connectivity of the replicated model stays finite, stays fixed to the original connectivity of the original model. Again, you can write your replicated partition function that will depend on M, and again, you can solve this model in the large M limit using a saddle point, and the saddle point solution is the Bethe lattice solution. So here I draw a portion of a Bethe lattice. The Bethe lattice is a special mean field lattice in which the local structure is tree-like. So in a Bethe lattice, two nearest neighbors are independent if the link between them is cut. So using this independence, you can solve almost any model on a Bethe lattice because you have this property. So the Bethe lattice is a mean field is a mean field model, but it's of a different kind with respect to the fully connected model. So this M-layer construction gives you the Bethe lattice solution in the M equal infinity limit. And the Bethe lattice has this nice property that there not exist loops of finite length. Then you can again look to the 1/m corrections to this saddle point solution. And then you realize that you obtain an expansion in the number of spatial loops. So in the limit m that it's equal to infinity, you don't have loops of finite length. On the original model that corresponds to m equal 1, you have loops at all orders, and the expansion in 1/m is an expansion in the number of topological loops. So I will skip all the computations. You can find them in the paper that I cited, but I will just explain you the flavor of the expansion and then the results in some nice examples. Okay, so you choose your observable, so for example, a 2-point correlation function, and then at order 1/m, your observable is just the sum of the contribution coming from all the linear path between spin I and spin j, thought as if they were on a Bethe lattice. So thought as the nearest neighbor spins were independent. So to compute the 1/m order of your observable, you should compute your observable on a line of length L on a Bethe lattice, and you should sum the contribution coming from all these linear paths. So this ZL is the number of such paths, and this A Bethe is the value of the observable computed on a Bethe lattice. This is the order 1/m. Then at order 1/m square, you should look to all the path that contains just one single topological loop. So the loop can have cubic vertices, like in this case, or also quartic vertices, so spins with 4 incoming lines. To compute the order 1/m square for your observable, you should sum the contribution coming from all these loops, and you should compute your observable on a loop thought as manually injected on a Bethe lattice. So again, here nearest neighbor should be thought as independent. Z again is the number of such loops, and it's known again. So A on a Bethe lattice is the only model dependent variable that you should compute. Okay, so why we need a new expansion? I mean, we have usual field theory, so why we need this new expansion around the Bethe lattice? Well, because the Bethe lattice is a different mean field model that has finite connectivity. In the case of strongly disordered system, finite connectivity is really a crucial property because it implies local fluctuations of observables. So on a Bethe lattice, a local observable has a non-trivial distribution, while on a mean field fully connected model, local observables have a trivial distribution that is picked around the global value of the observable. This means that, for example, fully connected model does not do not have heterogeneity, and this is really a crucial property when dealing with strongly disordered systems. Then our expansion around the Bethe lattice has also a larger range of applicability. For example, if you want to do an expansion around the mean field model, mean field fully connected model for the percolation problem, you cannot do it because percolation problems are not defined on fully connected lattices, while they are defined on the Bethe lattice. So, for example, you can recover all the critical exponent of percolations and also of bootstrap percolation in our expansion around the Bethe lattice. Then another useful point is that the Bethe lattice expansion starts from the microscopic model. You don't need to introduce a continuum field theory, and this is sometimes it's difficult to introduce a continuum field theory because you don't know, for example, the symmetries of your problem. Sometimes you don't need to know them in the case of the Bethe lattice expansion. Last but not least, usually in disordered system, you use the replica trick to do computations because this replica trick is a mathematical useful trick, but it's really difficult to decode the results of the replica trick, of computation done with the replica trick. On a Bethe lattice, you can do computation using the cavity method. That is another method, and you don't need the introduction of replicas. And this is really easier, and it has a clear physical interpretation. Okay, so let's look to the results of this expansion applied to some known models. So first example, the random field Ising model. The random field Ising model has this Hamiltonian, so you have a ferromagnetic coupling, and then you have a local field that is a random variable extracted, for example, from a Gaussian distribution. So you can write your field theory. It's a bit complicated because it's in replica space, and you have quartic interaction term, and you realize that you have two important correlation functions. The connected correlation function that decays in a way, and then the disconnected correlation function that decays differently. And then you can compute the first correction to the leading order term. You have some rules to construct your Feynman diagrams, and then you realize that at any order in perturbation theory, the field theory associated to the random field Ising model is equivalent to the field theory associated to the Ising ferromagnetic Ising model in d-2 dimensions. This is the so-called dimensional reduction property, and this is really nice because it says to you that you don't need to compute the field theory associated to the random field Ising model because everything you need to know is the Ising solution. Okay, well, so for example, you can compute the upper critical dimension, that is 6 in the case of the random field Ising model, because you know that the upper critical dimension of the Ising model is 4. So you just add 2 dimensions and you end up with dimension 6 for the random field Ising model. unfortunately, we know that dimensional reduction is wrong because, for example, it predicts a wrong lower critical dimension. So we know that perturbation theory around the fully connected solution is wrong somewhere, but we don't know how to cure it, how to find a way to have the right solution. Okay, so what we did in this paper is to analyze the expansion around the Bethe lattice. So at leading order, we obtain exactly the same results as the mean field fully connected field theory. And then we compute the first correction. We have two diagrams, a diagram with quartic vertices and the diagram with cubic vertices. The diagram with quartic vertices gives you exactly the same results as the one of the fully connected expansion. But then we have also this other contribution. So this cubic diagram that gives you something that is not null. So you have another contribution with respect to the usual fully connected expansion. So nice. This term is not there in the dimensional reduction scheme. So it could be the one that causes the dimensional reduction breakdown. But unfortunately, when you compute it, you find that it is there, but it's subdominant with respect to the usual fully connected diagram. So at least at first order, that is the one that we computed, it's not destroying dimensional reduction, this new term. However, it's there, and maybe at higher order, it could be that dimensional reduction breaks down because of these cubic vertices that are not included in the fully connected expansion. So in this case, the Bethe lattice expansion is different from the fully connected expansion. Not at first order, but it could be really a relevant difference at higher order. Then we looked at avalanches. Avalanches are a phenomenon that happens at t equals 0 in the random field Ising model. So you take your ground state, and then you change one spin, the spin I, for example, the one in red in the left picture. So you flip this spin, and then you look to all the other spins that flip because of the flipping of the I spin. So for example, on the right, I draw some spins that can flip because of the flipping of the I spin. And so you can measure the size of this cluster, and you call it an avalanche because it's a finite size. So you can realize that the size of these avalanches is proportional to the connected susceptibility. And then you can compute on your fully connected expansion the distribution of the size of the avalanches, and you find that the distribution according to the fully connected expansion is trivial. So the size of the avalanches is picked around a given value. But experimentally, we know that there is a non-trivial distribution of sizes of the avalanches. So, for example, you can compute it in d equals 3, and it's not a delta function. It's a non-trivial distribution. So you can compute the distribution of the sizes of the avalanches in the Bethe lattice expansion, and you can find a non-trivial distribution. So this is really a finite connectivity phenomenon that you cannot recover this phenomenon on using the fully connected expansion, but you can recover it using the Bethe lattice expansion because the Bethe lattice expansion has this finite connectivity. Okay, last example, the spin glass with field. So again, the spin glass has this Hamiltonian, so J are random couplings, and then you can add a field that is random or constant, it does not matter. So you can write your field theory. It's very complicated because it's in replica space. You have 3 masses, you have 8 couplings. Okay, you can compute your leading order for your connected correlation functions, and then you can compute the first correction that is due to cubic diagrams, so to Feynman diagrams with cubic vertices. And then you realize that this first correction becomes important at t equals 6. So the upper critical dimension in the fully connected expansion is 6. Below 6, this fully connected expansion does not find a spin glass phase transition. So this is the phase diagram of the spin glass in infinite dimensions of the fully connected model. You have this critical line that ends up at infinite field. And then you can draw the phase diagram of the same model, but on a Bethe lattice. And you can see that here your critical line ends at a critical critical field at t equals 0. So we perform our Bethe lattice expansion around this point. We compute the leading order, and again, it's exactly the same as the fully connected, as in the fully connected expansion. Then we compute the first correction, and surprisingly, this first correction is different from the fully connected expansion. It gives us an upper critical dimension equal to 8. So in this case, the Bethe lattice expansion really gives us a different prediction, an upper critical dimension that is equal to 8 instead of 6. So what next? We want to see if in this expansion we can find a spin glass phase also below 8. In the fully connected expansion, you cannot find a spin glass phase below 6. Here, with this expansion, we hope to find it, as we see in experiments, in numerical experiments, for example. So these are my conclusions. So the Bethe expansion is convenient when, in some cases, for example, for percolation, for the random field dicing model, for the spin glass in field at t equals 0. And there are a lot of nice line of research. So we want to look for a spin glass transition below the upper critical dimension in this expansion. And then we also want to apply this method to other models, for example, for Anderson localization or for glassy models. So I thank you for your attention, and that's all.
Thank you, Maria Chiara. We are running late, so we have time for one quick question. No questions?
If no question, I have one.
Okay, go on.
Thank you. No, I just wanted, it's a small technical question for Maria Chiara, but in the original formulation of Zingerstein, when you have a finite dimensional system, let's say in 2 dimensions, and then you pile on all the layers. But if I have 2 points on a given layer, which are at a certain distance, let's say L is the distance between the 2 points. When I do the M layer construction, this distance is not diminished. It remains at least L. So did I got it right, or
yes,
there are shortcuts?
No,
okay.
It remains the same distance, yes.
So the infinite connectivity is only among the different layers.
Yes, yes.
But on a given layers, it remains 2-dimensional.
Yes.
So there are only larger loops that you are adding. Is that right?
Well, not larger, because it's just at length, for example, 4, you can have a loop, no? In the case of the fully connected model. Here, for example, you have a loop.
No, but I mean loops among sites on the same layer. So if you go to the upper layer and then you have to come back, the loop is larger than the one you have.
Yes, but you have also the loops on the original model.
Yes, the loop of the original. And so the difference with the Bethe lattice with respect to this finite dimensional system.
There you destroy the loops on your original lattice. If you permutate all the links, you destroy the loops on the original lattice in the M equal infinity limit.
Okay. Thank you very much.
Here you don't destroy them.
Yes, thank you.
Okay, So thank you very much, Maria Chiara, and we can now pass to the next speaker, who is Diego Garlaschelli. And we are talking again about renormalization, but on multi-scale networks. So
yes, thanks a lot.
Sorry.
I think Maria Chiara should stop sharing, and then we can. Okay. Okay, here we are.
Okay, thanks a lot, Irene. So I'm trying to share the screen.
There is a problem because Maria Chiara, you need to stop. Okay, that's okay. Now it should be okay.
Can you see my screen now?
Yeah.
Okay. So thanks a lot. Well, first of all, to the organizers for taking up the challenge of organizing this huge event fully online. And well, so I have already seen other colleagues mentioning this, symbol of the conference in Parma. So let me add my own tribute to this in the bottom of the slide. So this talk is about multi-scale network renormalization. And I will have to explain what I mean by network renormalization throughout the talk, and also what I mean by this subtitle, scaling variance without geometry. So let me first thank Elena Garuccio, who is a PhD, former PhD in my group in Leiden, who contributed to this quite heavily, as well as Margherita Lalli, who is currently doing her PhD in my group at IMT Lucca, which is also working hard on this topic. So what's the starting point for this work? Well, the idea is that renormalization is rather simple when you have a regular lattice to renormalize, and it's well, way more complicated, if not undefined at all, when you have a complex network. So of course there are many rigorous definitions both of lattices and complex networks, but the intuition here is simple. So if you want, you can just pick up your favorite example that makes this intuition more alive. So, but what is the crucial point here? If we have regular lattices, then we are talking about networks, special types of networks, where nodes have their own coordinates. So, and coordinates can guide the renormalization of your network. So, for instance, you can easily identify which neighbors, who is neighbor of whom, based on how close the nodes are in some embedding space. So there is some embedding geometric space where nodes acquire coordinates, and then renormalization can largely proceed via these coordinates. Now, in general, complex networks don't have their own coordinates unless you impose that you're talking about a specific network that is somehow embedded. So there's a whole field of network geometry which views networks according to this picture. But I will try to highlight some perhaps a need of taking a more general approach to network renormalization. So, as I said, and also as the previous talk brilliantly illustrated, well, of course, if you have a regular lattice and then you have properties of your system like spins defined on this lattice, then it's rather easy to identify, say, the block nodes. Okay, so this can be largely guided by coordinates, and then what you need to do is to renormalize, say, your dynamic variables like spins. You have to decide what is the rule that you want to choose in order to define the spin of the coarse-grained node. So here it's rather natural the way you construct your renormalized system. Now, if you have a generic network, then many things become undefined. So what is the scale transformation in the first place? Because in networks, nodes can be connected to any other node in principle. There is, again, no necessary notion of coordinates. So how do you define block nodes? And then there are some specific properties which are typical of real real networks that make things even more complicated. So for instance, the fact that most networks are scale-free imply that if you look at the neighborhood around the node, you can have very different pictures based, well, depending on which is the node you are looking the rest of the network from. So for instance, if you look at the neighborhood of a hub, then you will see many nodes around. If you look at the neighborhood of an of a poorly connected node, you will see maybe one or a few connections around. So this already implies that there is no unique size if you want to introduce block nodes in the usual way. So for instance, by selecting the neighbors on the network of each node. So in a sense, the neighborhoods are not consistent from both sides of the picture, okay? And then there is the small wall property, which implies that typically there are very short paths connecting any pair of nodes. And this implies that you very easily saturate the network. So it's quite difficult to have renormalization schemes that you can iterate indefinitely because of this small wall property. And then maybe not so important issue, but for practical reason, this can be important. Sometimes you need to renormalize a network at different scales simultaneously. So for instance, you might need to work with a network where you have certain nodes defined at a given hierarchical level, like firms that are connected by, I don't know, business relationships. But then some other nodes in the same network may live at a different hierarchical scale. So they may be countries, for instance. And then you may need to incorporate links from one microscopic node, like a firm, to a macroscopic node, like a country. Or typically you have a rest of the world node that is often needed to balance your network in certain cases. So this means that if you want to think of a renormalization scheme that is consistent across all these situations, you need to reformulate or to wonder what a good choice would be. So for instance, original approaches relied mainly on the empirical fact that real networks are found to be scale-free, in the sense that the distribution of the number of connections per node follows a power law. And this led to an analogy with fractals, and somehow also suggested that box counting could be a kind of appropriate way to renormalize real networks. Other approaches assume a different property, for instance, the existence of communities or modules. And then in this case, you tend to coarse grain your network by considering block nodes as communities. And then there is another approach which insists that real networks have the properties they typically have, because you can assume that actually the nodes do have coordinates, only the embedding geometry is not flat, but it's hyperbolic. And then you can see that there are simple toy models that show that indeed many of the properties of real networks can be replicated in this case. But the problem with these approaches is that they are all making assumptions of some properties in the network that you need in order to justify the method itself. So you need either the model to have a scale-free degree distribution, or to have community structure, or to have this hyperbolicity. But most of all, they are not generalizable much beyond these assumptions. And in particular, the simplest case where you simply want to renormalize, again, your good old lattice is not contemplated. So these approaches are not reducible to arbitrary graphs, maybe even simpler graphs, including lattices. And then the idea of a multi-scale approach that I was mentioning before is not naturally implemented in these approaches. So this was the motivation basically for our approach. And then the idea is that basically all the problems that are there boil down to the difficulty of introducing a specific partition of nodes. So a sensible partition of nodes that works well when you want to renormalize a graph, a generic graph. So then we try to address the problem in, if you want, in a simplistic but then general way. So let's try to make it work for any partition. So given a node, given a network, we would like to see whether there is a scheme that allows us to describe this network, and this scheme will be a random network model, in such a way that for any possible partition of the nodes, you can consistently describe your system using the same random graph model, but with renormalized parameters. So in this way, by construction, we will try to avoid any structural assumption, so it will have to work also in the special case and traditional case, if you want, of lattices or even arbitrary graphs. Then, if you really need to work with special partitions, so if your real network that you're trying to describe with this method or model does have communities, for instance, then you can still implement some preferred partitions in a way that I will try to illustrate. So the basic idea is the following. So on the left, you may think of a graph, so a generic network that you're studying, and you're necessarily studying this network at some hierarchical level. So the nodes have their own identity, and this identity is defined at a certain level. For instance, firms, as I was saying before. Now, this is level L. Okay, and then you may want to consider a partition omega L, that maps these micro nodes into macro or block nodes. So this omega then creates, basically, it's nothing but a partition. So it's this circles on the left that become nodes on the right. And then the rule for the existence of a link is simple. I mean, if any of the pairs of nodes that were present across the two circles are connected, then there is one connection in the coarse-grained network. So the procedure is entirely binary. So we are not putting weights on the links. So you have a binary graph on the left and a binary graph on the right. So of course, the more you coarse-grained, the denser in general the network may become. Even if not necessarily. So you might engineer your partitions in a way that you avoid, for instance, by construction, creating a lot of links. But the idea is simple. So we want to have a binary description of the network that is consistent at all possible levels L. So there are relations, very simple relations between the adjacency matrix entries of the graph at level L and the same graph at level L+1. And this can be exploited to formulate a general problem and to solve. And the way we want to solve the problem is basically by saying, okay, we want to make the method intrinsically hierarchical, right? So this is what you normally do with the renormalization. So once you define the renormalization rule, you will iterate this potentially indefinitely. So until you basically explore all the possible hierarchical levels of your coarse graining. Since here we want to make this work for any partition, we can basically parameterize a full hierarchy of partitions in a dendrogram, for instance. So you may think of the original network as having nodes that are the leaves of this dendrogram. And then there will be a sequence of partitions that basically make these leaves merge into nodes at higher hierarchical levels. So whatever your nested hierarchy of partitions is, you can always represent this as a dendrogram. Now, automatically, this also tells you that you can imagine to cut the dendrogram at a given height, and then you will see the effects of renormalization at that particular hierarchical level. But you can also simultaneously cut the dendrogram at different heights for different branches. And in this way, you will basically implement this multiscale idea so that, for instance, for some of the nodes, you might decide to stick at a given hierarchical level, again, firms, but for other nodes, you want to coarse grain them a bit more, and for instance, cut the dendrogram at a level that represents countries, for instance, or the rest of the world node. Okay, so basically this multiscale partition is nothing but another partition. So since our goal is developing a method that works for any partition, this is automatically accounted for. So you can then block your nodes at with different sizes, and this should still be consistent. This is the goal of the approach. So this is basically to illustrate the idea. we want a random graph model to describe the entire process. So the random graph model means that there is a certain probability at level L that describes the occurrence of your adjacency matrix, A of L. So A is the adjacency matrix of the network at hierarchical level L. Now, you have the full probability distribution, so any graph in this ensemble is described by its own probability. And then once you specify omega, your partition, you have basically a projection. So possibly multiple configurations at level L will be mapped onto the same configuration at level L+1. So here in general, on the right, you have a smaller set of configurations with fewer nodes because it's the coarse-grained version. But then still you want to describe this through a random graph model because the randomness at level L will induce, given omega, so given the partition, will induce randomness at level L+1. So you still want this to be described by a probability. And now you want this to be renormalizable in the sense that you want your probability at level L to depend on a set of parameters. So theta L is the set of all parameters that define your random graph model. And then you want to have this defined consistently across levels. So you want that the functional form of the P doesn't change across levels. Only the parameters will be renormalized from one level to the next. Now, the property that this probability has to obey is that it should sum all the probabilities of the networks at lower levels that are mapped onto the same network at level L. So this is the meaning of the previous figure. And then you want to impose the scale invariance, basically. Now, if you make an assumption, so if you restrict yourself to the class of random graph models that have independent edges, then this probability P is factorized over all possible pairs of nodes by assumption. And then the question becomes, okay, now I want to find the scale invariant form of these local probabilities of connection. So this PILJL is the probability that node I is connected to node J at level L of description of your network. So this is basically, we're saying pairs of edges are statistically independent at any level of the hierarchy. Well, if you assume that they are independent at a microscopic level, they will remain independent at all upper levels. And then the question is, what is the functional form of Pij that enforces this scale invariance? Now, since you are selecting these models with independent edges, what sort of parameters do you allow inside the argument of this connection probability? Well, for sure, you will include one global parameter, delta L, which is controlling overall the value of these probabilities. So this means it's controlling overall the density of the network, the density of links. But then you may include the node-specific parameters, and this is in the family of fitness models that were introduced by Guido Caldarelli and collaborators. And these are called XIL for node IL. And then you may also want to include possible dyadic factors. So there may be higher order reasons why two nodes like to be connected or not being connected. And these are all encoded into, say, a matrix. This can include, for instance, membership to communities. This can include distances, like geographic distances between nodes. And as I said, this is the way you can force preferred partitions in a way into the model. But the model doesn't necessarily need these dyadic factors. It doesn't make much sense to include higher order parameters because in the end, it's a model with independent edges. So adding, say, triadic or higher order parameters is a bit strange. And it would be a kind of also of over-parameterizing your system. So if you make these assumptions that you want independence and then the parameters are global, node-specific, and dyadic, then there is a unique solution to this problem. So this is the form of the connection probability between node I and node J at level L. And you see that it has this form, 1 minus the exponential of minus delta, which is your global parameter, times the product of the fitness values at the two nodes at at the potential ends of the edge, times any function, which should be a monotonic function of these dyadic factors, okay? And then there are the renormalization rules that are attached to this solution. So this means that now if you want to go one level up in the hierarchy, so you go from level L to level L+1, you want your ensemble of graphs to be still described by this unique probability, but now with renormalized parameters. So how will delta renormalize in the new level of the description? Well, it turns out delta is a scale invariant. So delta doesn't change when you coarse grain. The fitness instead does change, and it's simply additive in the fitness of the nodes that are that end up in the given block node that you are defining. So again, you're free of deciding what your partitions are, and once you decide who goes into which block, then you have a new fitness for the entire block, which is simply the sum of the fitnesses of the participating nodes. And then the dyadic factors, say distances or whatever, follow this other renormalization rule at the bottom, which is nothing but a weighted average of these dyadic factors or distances within the blocks. And the averaging is done by weighting them with this fitness. So basically it's a fitness weighted average. Okay, so these are the basic rules of the game. And then one can make some comments, but I want to maybe be faster on this part. I want to show you applications rather. So when we think about applications of this model, we can consider at least two scenarios. So one is the scenario that we call the quenched case. So in the quenched case, we interpret xi, so the fitness of every node, as a parameter that is fixed forever. So it's something that is identifying that node. So it's different for different nodes, and it could be, for instance, something that you measure from empirical data about that node in the network. And indeed, I will show an application where the fitness is taken to be the GDP of a country, so where nodes are countries and links are import-export relationships between countries. So this is the international trade network that has been studied a lot in this fitness model framework. So now, every node is characterized by its own GDP, something that you measure clearly from empirical data. And then the question is this model a good model for that network? And especially, how does it work upon coarse graining the network by considering, say, blocks of countries and the corresponding links? And then there is the approach that we call the annealed approach. And that's the case where now you think of the fitness variable itself as something that can be resampled at every level. So you allow for randomness in the fitness itself, so that there are two sources of randomness. Fitness is drawn from some probability distribution, and then conditional on the fitness, you generate your configurations of the random graph. And you still want this, say, augmented picture to be a scale invariant. So now you have to enforce some property at the level of this distribution of the fitness. And if your requirement is, again, the scale invariance of the entire picture, you are bound to select Levy stable or alpha stable, the probability distributions for the fitness. So then in that case, you have to work out, if you can, some calculations that describe the resulting ensemble of random graphs interpreted as averaging over the fitness as well. Okay, so let's consider the quenched application first, very quickly. So as I said, the system we are applying this.
I'm sorry to interrupt, Diego, but we are far beyond the
oh, sorry. Okay,
the time schedule. So I just want you to let you know that you should hurry. Okay.
Okay. Thanks a lot. Okay, so very simple. Just in pictures, what I said. You'll assign every node a fitness, which is the empirical GDP, and then you find the correct parameter delta that is controlling for the right density, and you simply track across renormalizations of the network whether you are still guessing the correct density. And you can do the same for the assortativity of your network, the clustering of your network across hierarchical levels. And it seems to work very well. Also considering how individual node properties evolve upon normalization. So for instance, average nearest neighbor degree and clustering coefficient of individual nodes. So just last 10 seconds, in the annealed case, instead, as I said, you are bound to consider Levy-stable fitness distributions. And it turns out, through some calculations that are still possible in this case, that you basically generate scale-free networks, in a sense, automatically by considering Levy-stable fitness. So thanks a lot. And let me then conclude with a reference if you're interested. And let me just mention that there are PhD openings, both at IMP Lucca and at the National PhD in Artificial Intelligence. So if you can, say, disseminate this in your network, it would be good if you have especially good master students that are interested in doing a PhD. Thanks a lot, and sorry for taking too long.
Okay, thank you. We are really late, so if there is any quick question, otherwise, I mean, people can talk with Diego afterwards. Any question? Okay, so thank you very much, and I'm sorry I had to interrupt, but we are really late. Oh, and thank you very much to all the speakers of this afternoon session. And I think we can now probably stop the recording, but maybe if okay, great. So thank you very much to all participants, and I think we can conclude this session here. Thank you very much.
Thank you, everybody.
Thank you.
Thank
you. See you tomorrow.
See you tomorrow.
Yeah.
We remind you that
the
poster session tomorrow in the morning and the main session in the afternoon at 2:30. Bye.
Bye, bye, everybody.
Bye.
See you tomorrow.
Ciao.
Ciao, ciao. Ciao.
Bye, bye.
Ciao.
Bye, everybody.
Almeno ci si vede.